Look up on a dark night, far from city lights, and you'll see it, a glowing band stretching across the sky like spilled milk. Ancient people thought it was a river, a path for gods, or the backbone of night. But here's the crazy part. That bright band has dark scars, ragged tears that slice through the light. For thousands of years, nobody knew what those dark rifts were hiding. Today, we're pulling back the curtain on the Milky Way's biggest secret. That glowing band is our galaxy, the Milky Way. From Earth, we see it edge on, a dense, star-packed core surrounded by swirling arms. But something's wrong. Dark, jagged lanes cut through the brightness like shadows. Early skywatchers noticed them. They sketched them, named them, and wondered why the gods would leave such scars in the sky. This isn't just a pretty light show. It's a puzzle that took centuries to solve, and the answer changed everything we thought we knew about our cosmic home. Here's the problem. For most of human history, we had no idea what we were looking at. The bright band? Easy to see. But those dark rifts? They looked like empty voids, holes in the fabric of the sky. Ancient cultures had wild guesses. Some said they were rivers of emptiness. Others thought they were smoke from celestial fires. Even when telescopes were invented, the dark lanes stayed stubbornly dark. How do you study something that swallows light? How do you map what hides in plain sight? This mystery stumped astronomers for generations. The dark rifts weren't just curiosities. They were clues to the galaxy's hidden structure, and cracking them meant understanding our place in the cosmos. Let's start with what we actually see. On a clear night, away from city lights, the Milky Way dominates the sky. It looks like a hazy river of light, thicker and brighter toward the constellation Sagittarius. That's the galactic center, the heart of our galaxy, packed with stars, gas, and dust. But running through it are dark lanes, like ink spilled on water. The most famous is the Great Rift, a series of dark clouds that split the Milky Way from Cygnus all the way to the southern sky. To the naked eye, it looks like the galaxy is torn in two. Ancient people noticed this immediately. The Inca called the dark areas Yacana, a llama whose body was formed by the dark lanes. Aboriginal Australians saw it as a river in the sky, with the dark patches as deep pools. In Eastern Europe, the dark rifts were called the dark scythe, cutting through the celestial river. But no one had a clue what caused them. Some thought they were literal holes, empty spaces where stars were missing. Others imagined they were cosmic fog, blocking our view. Fast forward to the 1600s. Galileo pointed his telescope at the Milky Way and made a stunning discovery. The Milky Band wasn't a cloud or liquid. It was made of countless individual stars. His telescope resolved the haze into points of light, proving the galaxy was a collection of suns. But the dark rifts, they stayed dark. Even with better telescopes, those areas remained stubbornly empty. Why? The answer came slowly. In the 1700s, astronomers like William Herschel started mapping the sky in detail. He noticed that stars seemed to cluster in certain patterns, and the dark lanes often marked boundaries between star clusters. He theorized that the dark areas weren't empty. They were filled with something that blocked light. But what? By the 1800s, astronomers had a new tool: photography. Long exposure images of the Milky Way revealed the dark rifts in stunning detail. They weren't random smudges. They were intricate, cloud-like structures. Some looked like twisted ropes, others like billowing smoke. Photographers like John Herschel, William's son, and Isaac Roberts captured images that showed the dark lanes had texture and depth. They weren't holes, they were something solid. The breakthrough came in the early 1900s with the work of Edward Emerson Barnard. He spent decades photographing the Milky Way and cataloguing dark nebulae, clouds of gas and dust so dense they blocked the light from stars behind them. Barnard realized the dark rifts weren't empty space. They were cosmic dust clouds. And not just any dust. Fine particles of carbon and silicate floating in space, thick enough to absorb starlight completely. Barnard's catalogue of dark markings in the sky, published in 1919, listed 182 dark nebulae. The most famous is Barnard 68, a near-perfect sphere of darkness that looks like a hole in the sky. But it's not empty. It's a cloud of gas and dust so dense it's collapsing to form new stars. The dark rifts in the Milky Way are just larger versions of these clouds, stretching across light years. But why are they there? The answer lies in the structure of our galaxy. The Milky Way is a barred spiral galaxy, with a central bulge surrounded by spiral arms. From our position inside one of those arms, we see the galaxy edge on. The bright band we see is the combined light of billions of stars in the galactic disk. The dark rifts, they're giant molecular clouds, vast, cold regions where gas and dust are so thick they block visible light. These clouds are the birthplaces of stars, but they're also cosmic curtains, hiding the galaxy's core from view. The thickest part of the dark rifts lies toward the galactic center, in the direction of Sagittarius. That's where the dust is densest, forming what astronomers call the zone of avoidance. For decades, this region was nearly impossible to study because the dust blocked everything. We couldn't see the galactic center, we couldn't map the spiral arms, and we couldn't understand our galaxy's true shape. Then came radio astronomy. In the 1930s, Carl Jansky discovered that radio waves could pass through dust unimpeded. Suddenly, astronomers could see through the dark rifts. Radio telescopes revealed the structure of the Milky Way's center, showing a dense core of stars and gas. Later, infrared and X-ray telescopes peeled back more layers, revealing supermassive black holes, star clusters, and regions of intense star formation, all hidden behind the dark lanes. Today, we know the dark rifts are more than just dust clouds. They're dynamic regions where stars are born and die. The Great Rift, for example, contains several star-forming regions, including the Eagle Nebula, famous for the Pillars of Creation, and the Omega Nebula. These areas glow in infrared and radio light, even though they appear dark to our eyes. The dust itself is fascinating. It's not like the dust under your bed. It's microscopic particles, often coated in ice, floating in space. When these particles clump together, they form dense clouds that can stretch for hundreds of light years. Some clouds are so cold, just a few degrees above absolute zero, that molecules like carbon monoxide and water ice can form. These molecules are the building blocks of planets and life. But the dark rifts also hide dangers. The same dust that blocks starlight can also obscure threats like near-Earth asteroids or supernovae. In 1987, a supernova exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. It was visible to the naked eye, but if it had happened behind a dark rift, we might have missed it entirely. Now for the biggest twist. Those dark rifts aren't just blocking our view. They're hiding the most violent and mysterious part of our galaxy. In the 1990s, astronomers pointed infrared telescopes toward the galactic center and found something astonishing. Behind the thickest part of the dark rifts, in the constellation Sagittarius, lies a supermassive black hole called Sagittarius, a star. It's 4 million times more massive than our Sun, and it's devouring gas and stars. The dark dust lanes act like a veil, hiding this cosmic monster from view. Without radio and infrared telescopes, we'd never know it's there. But here's the mind-blowing part. The same dust that hides the black hole is also feeding it. Friction in the dust clouds causes material to spiral inward, creating a swirling disk of superheated gas that glows in X-rays. The dark rifts aren't just curtains, they're the black hole's dinner plate. So the bright band of the Milky Way and its dark rifts tell a story of discovery. Ancient people saw the glow, but couldn't explain the shadows. Early telescopes revealed stars, but couldn't penetrate the darkness. It took radio astronomy and space telescopes to finally see through the veil. The dark rifts aren't holes or voids. They're vast clouds of gas and dust, the raw material for new stars and planets. They hide the galaxy's core, including a supermassive black hole that shapes our cosmic neighborhood. What looked like scars in the sky are actually the fingerprints of creation and destruction, marking where the Milky Way is constantly being reborn. It took a new kind of vision to pierce the heavy veil cloaking the Milky Way's heart. For centuries, the galaxy's center lay hidden behind dark swathes of cosmic dust, invisible to any optical telescope. But in the mid-20th century, astronomers began turning sensitive infrared eyes toward this mysterious region. Infrared light, with its longer wavelengths, can slip through dust that stops ordinary starlight. At certain infrared wavelengths, the interstellar murk becomes more transparent, opening a window through the dust. Peering through this infrared window, scientists caught their first glimpse of what lay at the galaxy's core. Instead of empty darkness, they found a crowded city of stars sparkling behind the obscuring clouds. For the first time, the heart of our galaxy was revealed not as a void, but as a vibrant hub of starlight. In the late 1960s, a pair of pioneering astronomers scanned the galactic center in infrared and discovered something astonishing. Where visible light telescopes saw only a blank void, the infrared detector revealed swarms of stars huddled together in an extraordinarily dense cluster. This was a realm teeming with stars packed far closer than those in our Sun's neighborhood. It was as if an entire metropolis of suns had been hiding just out of sight, concealed by dust but glowing warmly in infrared. The discovery was revolutionary. These astronomers had effectively lifted a corner of the galaxy's dusty curtain. They had overcome a dimming of starlight so severe that the galactic center's stars were rendered invisible in ordinary light, diminished by a factor of billions. Yet in infrared, those same stars shone through faintly but unmistakably. By using light near 2 microns in wavelength, deep red beyond what our eyes see, they pierced a gloom that had made the central region's light only a billionth as bright as it truly is. Long before infrared light opened our eyes to the galactic nucleus, another strange signal had already whispered of the hidden core. In the early 1930s, a young radio engineer named Carl Jansky was investigating static that interfered with radio communications. Using a rotating antenna in a New Jersey field, he heard a persistent hiss of unknown origin. Day after day, this faint static appeared and peaked at a certain time, drifting slightly with the seasons. At first, he suspected it might be thunderstorms or the sun, but the timing didn't match any daily cycle on Earth. Instead, Jansky realized the mysterious static followed the stars. It repeated every 23 hours and 56 minutes, the length of a sidereal day. With the help of astronomers, he traced the signal to the southern sky, toward the heart of the Milky Way in the constellation Sagittarius. In 1933, he announced that he had found radio waves coming from the center of our galaxy. This revelation marked the birth of radio astronomy. For the first time, humanity had detected a signal from the stars that was not visible light. Jansky's discovery made headlines. Our galactic center, though hidden in darkness, was emitting a radio whisper across space. It was a faint murmur from the Milky Way's heart, hinting at energetic processes that no optical telescope could see. In the years that followed, a handful of enthusiasts built the first rudimentary radio telescopes and confirmed that the Milky Way glowed in radio waves. They found the strongest radio emission came from the direction of Sagittarius, exactly where Jansky had pointed. After World War II, radio astronomy blossomed, and scientists began mapping the sky in this new spectrum. In the early 1950s, astronomers in Australia zeroed in on the Sagittarius region and identified a particularly intense concentration of radio waves coming from the very center of our galaxy. They named this source Sagittarius A-A because it was the first and brightest radio source found in that constellation. To these early radio astronomers, Sagittarius A was a revelation. The Milky Way's nucleus was not silent at all, but broadcasting a signal we could now detect. Here was a clue that something energetic lurked in the darkness, something powerful enough to send out radio waves through the obscuring dust. Throughout the 1960s, as radio telescope arrays improved, the picture of Sagittarius A grew clearer. They discovered that the radio glow from the galactic center was not a single simple object, but a complex region. There were hints of multiple overlapping components, vast clouds of ionized gas, remnants of past stellar explosions, and in the middle of it all, a compact source of radio emission that defied easy explanation. Astronomers began to suspect that at the core of Sagittarius, A lay a very small, bright source embedded within the broader radio glow. Later, this would be called Sagittarius A star, the very heart of the radio emission. But in those early days, it was simply an intriguing mystery. By the end of the 1960s, the galactic center had been detected in both infrared and radio waves, each revealing different facets of this hidden realm. Yet more secrets were locked behind the cosmic fog, waiting for the right tools to uncover them. The dust was no longer an absolute barrier, but the galactic center still held mysteries that infrared and radio alone could not resolve. New telescopes, reaching to even shorter and longer wavelengths, would soon push the boundaries and break through the remaining darkness. As technology advanced, astronomers continued to peel away the galaxy's obscuring veil by probing new wavelengths of light. In the 1970s and 1980s, infrared astronomy leapt forward, providing ever clearer views of the hidden core. Sensitive detectors and airborne observatories, lifted above much of Earth's atmospheric water vapor, allowed deeper infrared imaging. What these near-infrared and mid-infrared observations revealed was a bustling central region aglow with warmth and energy. For the first time, space-based infrared telescopes like the IRAS satellite and specialized ground telescopes could map the galactic center without the interference of the lower atmosphere. They found that the nucleus of the Milky Way was one of the brightest infrared sources in the sky, packed with hot dust and myriad stars whose collective glow heated their surroundings. Enormous clouds of dust that hid the core in visible light now themselves became visible at mid-infrared wavelengths, glowing as they absorbed and re-radiated the energy from the crowded stars. In false-color infrared images, the central region transformed into a vivid tapestry. Clusters of stars shining through in near-infrared, and swirls of warm dust glowing red and orange in the mid-infrared. Meanwhile, at even longer wavelengths approaching the sub-millimeter range, new observatories began capturing the faint whisper of cold dust and molecular gas. In the 1990s, telescopes like the James Clerk Maxwell Telescope and others peered into the sub-millimeter spectrum and uncovered an essential piece of the puzzle. They detected a ring of dense material circling the center, a reservoir of cold molecular clouds and dust known as the central molecular zone, shining at these wavelengths. At sub-millimeter wavelengths, the very heart of the Milky Way also lit up. A compact source at the center emitted a bright glow, hinting at superheated material close to the central engine. Beyond the infrared and radio, astronomers also turned to the opposite extreme of the spectrum, the penetrating gaze of X-rays. High-energy X-rays can slice through intervening gas and dust, and beginning in the late 20th century, X-ray observatories lifted the final veil, obscuring the galactic center. Early X-ray detectors in the 1960s and 1970s caught hints of energetic activity from the Sagittarius region. But the true X-ray portrait had to wait for later technology. When NASA's Chandra X-ray Observatory and Europe's XMM Newton began focusing on the Milky Way's core around the year 2000, they revealed a sight unlike any seen before. The X-ray images showed a tumultuous scene of high-energy phenomena. A diffuse glow of X-rays permeated the central region, evidence of million-degree gas, likely heated by shocks and past outbursts. Dozens of mysterious X-ray point sources dotted the area, possibly neutron stars, black holes, and other exotic remnants crowded around the center. And at the very heart, Chandra detected a faint but persistent X-ray source, right where Sagittarius A lies, occasionally flaring up in bursts of brilliance. With near-infrared, mid-infrared, sub-millimeter, and X-ray eyes, all trained on the galactic center, the once invisible core was becoming a rich panorama of data. Each wavelength uncovered a different layer of the story, from the crowded stellar heart to swirling dust clouds, from cool molecular reservoirs to searing hot plasma. What was once merely an area of darkness on the sky had now been transformed into one of the most scrutinized and fascinating regions in the entire galaxy. Yet, even as the fog was broken, a deeper understanding of what powered this central hub still eluded astronomers, beckoning them onward. Even as new wavelengths unveiled the galactic center, astronomers worked to chart the broader structure of stars surrounding the core. This central huddle of stars, the galactic bulge, extends thousands of light-years around the nucleus and had long been difficult to map from our vantage point within the disk. Throughout the late 20th century, deeper surveys in infrared light allowed scientists to count stars across the bulge and peer through the dust hiding them. As they assembled these star maps, a clearer shape began to emerge from what had once been a blurry, obstructed view. It turned out the Milky Way's bulge was not a simple sphere of stars, as once thought, but an elongated formation, a bar-like structure at the galaxy's center. Observations from the COBE satellite in the 1990s first hinted at this, showing a brightness asymmetry that suggested more stars on one side of the center than the other. Later surveys using ground-based telescopes confirmed the bulge's triaxial shape. Millions of stars were mapped, and their distribution revealed a cigar-shaped stellar hub, like a cosmic bar stretching across the central region. To measure the bar and its angle, astronomers turned to a special kind of star as their guide, the red clump giants. These aging red stars have a nearly standard intrinsic brightness, making them reliable beacons for gauging distances. By comparing the apparent brightness of red clump stars in different parts of the bulge, researchers noticed something intriguing. In certain directions, the red clump stars appeared in two distinct groupings of brightness, one slightly nearer and one slightly farther. This double clump was a telltale sign that the bulge was shaped like a bar seen at an angle. We were seeing the near end of the bar and the far end, each with its cluster of red clump stars. From such data, astronomers deduced that the galactic bar is tilted relative to our line of sight, with one end closer to us in the northern galactic sky and the other end farther away in the south. The bar was estimated to stretch roughly tens of thousands of light years across, and to be oriented about 30 degrees from our viewpoint. This revelation transformed our mental picture of the Milky Way's core. No longer a symmetric bulge, but a dynamic, triaxial structure, a stellar bar underpinning the galaxy's central architecture. The existence of this bar explained many things. It aligned with observations of how gas moves in the inner galaxy and placed the Milky Way firmly among the ranks of barred spiral galaxies common in the universe. With the bulge and bar mapped out, astronomers had a better context for the center itself. They now understood that the nuclear region sits at the nexus of a grander bar structure funneling stars and gas inward. It was as if the Milky Way had a hidden skeleton in its central regions, only visible once the dust was penetrated and the stellar distribution laid bare. Having charted the bulge and bar on galactic scales, astronomers could next turn their attention to the heart of that structure. There, in the innermost few light years, was a tightly bound urban core of stars, the nuclear star cluster, waiting to be explored in detail. At the center of the Milky Way's bulge, nestled deep within the bar, lies an extraordinary gathering of stars. This is the nuclear star cluster, a dense, tightly bound swarm of millions of stars crammed into the volume of space only a few light years across. If the broader bulge is the city surrounding the galactic downtown, then the nuclear star cluster is the glittering downtown core itself. Here, stars crowd together in numbers and proximity found nowhere else in the galaxy. In this cosmic downtown, night never truly falls. Surrounded by so many neighbors, each star's sky would be ablaze with countless brilliant lights. The density is almost unimaginable. In some parts of the cluster, stars can be only a few trillion miles apart, practically rubbing shoulders on astronomical scales. By comparison, our Sun's nearest neighbor star is over 4 light years away. In the galactic center, a star might have dozens of neighbors within that same distance. Most of the stars in this crowded cluster are old, ancient red giants and tired sun-like stars that have likely drifted inward over many generations. They form a diffuse, golden glow when seen in infrared, a broad background of aged starlight. But mixed in are some surprising youngsters, a sprinkling of massive, hot stars and even stellar infants that have no business being in such a tumultuous place. Their presence hints that star formation has occurred here relatively recently, despite the harsh conditions near the galactic center. Embedded within this stellar metropolis is the very dynamical center of the Milky Way, the pivot point around which everything in the cluster orbits. All the stars here are in rapid motion, careening around unseen gravitational depths at hundreds of kilometers per second. The concentration of mass at the core is so great that it holds these speeding stars in thrall, forcing them to loop in tight, fast orbits. When astronomers first measured the velocities of stars in the nuclear cluster, they were astonished at how quickly those stars were moving, a clear sign of an immense unseen mass pulling on them. This unseen central mass resides at the focus of all those stellar orbits. It is effectively the anchor of the nuclear star cluster. In later years, astronomers would identify this mass more concretely. But even early on, the motions in the cluster suggested that something very massive and compact lurked at the core. The nuclear star cluster itself orbits this hidden mass like a swarm of fireflies spiraling around an invisible flame. It is the stellar embodiment of the Milky Way's hidden heart, shining and circling in the darkness. Stars are not the only inhabitants of the galactic center. Surrounding the nuclear star cluster is a vast and turbulent expanse of gas and dust, forming a distinctive ring around the innermost region. Astronomers call it the central molecular zone, a cosmic donut of dense molecular clouds orbiting the center of the Milky Way. This zone extends a few hundred light-years from the core and holds an enormous reservoir of the galaxy's interstellar fuel in a relatively tiny volume of space. The molecular clouds in this ring are colossal, some containing millions of times the mass of our Sun in gas. They are also extraordinarily dense and turbulent. Clouds careen around the galactic center at speeds of tens of kilometers per second, colliding and shearing under the gravitational stress of the central mass and bar. The result is a roiling, dynamic environment where clouds are compressed, stretched, and sometimes triggered into forming new stars. Within these clouds lies a chemistry lab on a galactic scale. The central molecular zone is so named because its gas is primarily molecular, and it hosts a rich variety of chemical compounds. Radio telescopes, by detecting spectral fingerprints, have identified over 100 different molecules in these clouds, from simple carbon monoxide and ammonia to complex organic molecules. One giant cloud, known as Sagittarius B2, for example, is famous for containing a menagerie of molecules, including alcohols, formaldehyde, and even amino acid precursors. The conditions near the galactic center contribute to this chemical complexity. The gas is dense and often shock-heated by cloud collisions, providing energy to drive unusual reactions. There are also strong magnetic fields and cosmic rays bathing the region, which can alter molecules and spur exotic chemistry not seen in calmer galactic neighborhoods. To astronomers, the central molecular zone is like a cauldron, constantly stirred and bubbling with rare ingredients, offering clues to how complex chemistry unfolds in space. This turbulent ring is not just a backdrop. It is also the central engine's fuel depot. Gas from the bar flows into the central molecular zone, and some of it spirals inward from the ring toward the very center. This inflow may feed whatever lies hidden at the core, perhaps explaining the sporadic outbursts and flickers that astronomers have caught coming from the galactic center. In essence, the central molecular zone is both a buffer and a supplier, regulating the diet of the Milky Way's central engine. For the most part, the Milky Way's central black hole, or whatever massive object lurks there, is remarkably quiet. Unlike the voracious quasars seen in distant galaxies, our galactic center does not constantly blaze with high-energy light. Instead, it murmurs in the radio and occasionally whispers in X-rays, punctuated by only the rare outburst. But those outbursts, when they occur, have given astronomers fascinating glimpses into the behavior of our galaxy's hidden powerhouse. In the late 20th century, radio astronomers monitoring Sagittarius A star noticed slight variations in its emission. On some days, the radio output from the center would be a bit brighter or dimmer than usual. Subtle fluctuations, like the flickering of a faraway ember. These changes were modest, hinting that the central source was gently variable rather than utterly steady. It wasn't until the new millennium, however, that the galactic center's true fireworks were caught in the act at higher energies. In 2001, the Chandra X-ray Observatory detected an unexpected flash from the direction of Sagittarius A star. Within just a few minutes, the X-ray brightness of the galactic center shot up by 100-fold, then gradually subsided over the next hour. Astronomers had witnessed a genuine flare, a sudden release of energy from the otherwise faint central source. Since that first observation, numerous X-ray flares have been recorded, some smaller and some rivaling that initial burst in intensity. Not long after the X-ray flares were discovered, infrared telescopes also picked up rapid flickers of light from the galactic center. At infrared wavelengths, where we can directly track the motions of stars near Sagittarius. A star, Astronomers saw occasional blazes of emission that appeared and faded within an hour or two. These infrared flares often coincided with X-ray bursts, confirming they came from the same underlying event, likely material suddenly heating and glowing as it fell toward the central object. The flares in infrared allowed scientists to pinpoint their exact origin at Sagittarius A star, as the region would momentarily outshine even the dense star cluster around it. Between these dramatic flares, the central radio source emits only a low murmur. Sagittarius. A star's baseline radio emission is steady and relatively weak, as if the black hole is idling in a state of near dormancy. It's a far cry from the continuous roar of an active galactic nucleus. This faint, steady glow is the whisper of the central engine, the gentle radio noise that was first heard by Jansky and others, now understood as the quiet glow of superheated electrons swirling in a weak accretion flow. Yet there are clues that this quiet object was not always so subdued. Astronomers have found indirect evidence of powerful outbursts in the past. For instance, surrounding gas clouds carry an X-ray sheen, as if lit up by a burst of radiation that passed through them some time ago. And towering above and below the galaxy are giant bubbles of energetic particles, the so-called Fermi bubbles, believed to be remnants of an episode when the center of our galaxy flared up tens of millions of years ago. These are cosmic echoes, whispers of past firestorms from the heart of the Milky Way. In our present era, however, the central beast slumbers lightly, stirring only occasionally. Each time it does stir, each flicker of radio emission or flash of X-rays, astronomers gain a bit more insight into the extreme environment just outside the event horizon. The flares are like brief beacons in the dark, illuminating the processes by which matter falls in and energy is released. They remind us that even a sleeping dragon can still breathe fire now and then, offering a tantalizing hint of its true power. With so many different eyes trained on the galactic center, radio, infrared, X-ray, a crucial task emerged, making sure everyone was looking at the same thing. Early on, the various images of the center did not line up perfectly. A bright spot in a radio map might not obviously correspond to a feature in an infrared image filled with stars. To truly understand the central engine, astronomers needed to pinpoint its location across all wavelengths and reference frames. One challenge was the sheer crowding of the region. In infrared, the galactic center is a dense star field. Hundreds of stars appear in the central arc second on high-resolution images. In radio, by contrast, Sagittarius A star stands out as a compact source amid a smoother background of diffuse emission. Linking the two views was like overlaying two very different maps of a city, one showing bright city lights at night, the stars, and another showing a single radio beacon in the same city. It wasn't immediately obvious which star, if any, corresponded to the radio beacon of Sagittarius A star. The breakthrough came by using precise astrometric reference points and timing the flares. Astronomers identified a handful of infrared emitting objects whose positions could also be tied to features in radio images. For example, orbiting stars that could be related to known radio masses in the region. Using these as landmarks, they calibrated the coordinate systems of their telescopes. Then, during one of the detected flares, they observed it in both X-ray and infrared simultaneously, confirming that the burst of light in infrared was coming from the exact same spot as the X-ray flash and the known radio position of Sagittarius A star. It was a triumphant alignment of cosmic maps. The mysterious radio source, Sagittarius A star, the pinpoint infrared flares, and the weak X-ray flicker were all one and the same object. This meant that the point around which the stars were seen to orbit, the dynamical center determined from infrared stellar motions, coincided exactly with the compact radio source. In other words, the invisible gravitational center of the Milky Way and the observed radio/X-ray emitter were pinpointed to the same location in space. With this alignment, astronomers had essentially put a crosshair on the galaxy's nucleus. They now knew precisely where the beating heart of the Milky Way resides. In fact, today, Sagittarius, a star, serves as the defining reference for the center of our galaxy, the 0 point of the Milky Way's coordinate system. By bringing all observations onto the same page, scientists set the stage for the most compelling evidence yet that this pinpointed location harbors a truly extraordinary object. By the end of the 20th century, a picture was emerging of something extraordinary at the center of our galaxy. All the evidence gathered, the crowded stars moving at extreme speeds, the intense but compact radio source, the occasional high-energy flares, pointed toward a single explanation. Astronomers began to strongly suspect that the hidden engine driving all these phenomena was a supermassive compact object, most likely a black hole of millions of solar masses. What else could pack so much mass into such a tiny space and remain invisible, yet occasionally erupt with energy? The idea of a black hole at the galactic center wasn't entirely new. As far back as the 1960s and 70s, a few visionary astronomers had speculated that our Milky Way might harbor a supermassive black hole, akin to the power sources of quasars, but in a quiet state. Early radio observations had hinted at a massive concentration, and theoretical work suggested that a large black hole could remain dormant if it had limited fuel. But it was in the 1990s that this hypothesis started turning into conviction, thanks to mounting observational evidence. One critical line of evidence came from measurements of how fast objects were orbiting the center. Using infrared spectroscopy and later precise imaging, scientists measured the velocities of stars and gas swirling around the nucleus. They found that the closer in one looked, the faster things were moving. This indicated a very steep increase in enclosed mass toward the center, as if an extremely massive object were sitting in the middle, pulling on everything around it. For example, by analyzing the motions of ionized gas clouds and groups of stars near Sagittarius A star, researchers deduced that some 3 to 4 million solar masses must be confined within a region no larger than a few light weeks across. Such an incredible density was hard to explain by any cluster of normal objects. Any collection of stars or neutron stars squeezed into that volume would either collapse rapidly or produce prodigious light as a quasar. The most plausible explanation was a single supermassive black hole. Its gravity could bind the stars and accelerate them to the observed speeds, all while the object itself remained dark except for the occasional flare from infalling matter. Another piece of evidence was the size of the radio source, Sagittarius A star itself. By using very long baseline radio interferometry, astronomers could measure the apparent size of A star on the sky. They discovered it was astonishingly small, on the order of only light minutes across, smaller than the orbit of Mercury. Containing a few million suns within such a tiny radius pointed again to an object that wasn't a cluster of stars or anything else known, reinforcing the black hole interpretation. By the time all these puzzle pieces were assembled, rapid stellar orbits indicating a massive central gravitating point, the incredible concentration of mass, the diminutive size of the radio source, the scales had tipped firmly toward one conclusion. The galactic center was almost certainly a supermassive black hole, making our Milky Way a quietly active galaxy with a sleeping giant in its core. In scientific meetings and papers of the 1990s, the term massive compact object was often used, as caution lingered in calling it a black hole outright. Yet more and more astronomers came to believe that is exactly what it was. A black hole on the order of a few million times the Sun's mass. Still, at the turn of the century, this remained an inference, extremely convincing, but awaiting direct proof. That proof would arrive in the early 21st century, when astronomers managed to trace the actual paths of individual stars whipping around the unseen mass. Those results would ultimately silence any remaining doubt. But even before then, the evidence had become overwhelming. The Milky Way's hidden engine was no longer just a mystery. It was strongly presumed to be a supermassive black hole, quietly lurking at the galaxy's heart and occasionally reminding us of its presence with a flicker or a flare. For decades, the very center of our Milky Way was shrouded in mystery. When astronomers looked toward the constellation of Sagittarius with ordinary visible light telescopes, they saw almost nothing. A deep darkness where the galaxy's nucleus should be. Some astronomers, notably in the 1960s, even suspected a hidden powerhouse lay there, perhaps even a black hole, to explain odd observations. But without proof, it remained speculation. Radio telescopes had picked up a strong, compact source of radio waves from that region, later dubbed Sagittarius A, hinting at something energetic. Yet to human eyes, and even the finest optical instruments, the galactic heart remained invisible, cloaked by dust and distance. Some scientists hypothesized that a supermassive black hole might lurk there. Ideas floated as early as the 1960s to explain unusual motions of radio-emitting gas at the nucleus. But it was purely conjectural, without direct evidence. High above the crowded stellar bustle of the Milky Way's core, astronomers fixed their gaze on this shadowy realm veiled in darkness. Invisible to ordinary eyes, the galactic center is obscured by thick interstellar dust that blocks visible light. It was like trying to peer through a smoky veil. The central region lay hidden behind billions of stars and clouds. But astronomers found a way to lift the veil, observing in infrared light, which can slip through the dust. In the infrared, a stunning scene emerged gradually into view. There, in the heart of the darkness, a swarm of bright young stars appeared, gathered around what seemed to be an empty patch of space. These stars were not static. They moved in a way that defied expectation, hurtling around an unseen something, as if dancing to the gravitational pull of a massive but invisible partner. Getting this clear view was no simple task. From ground-based telescopes, even infrared images were blurred by Earth's turbulent atmosphere, which makes stars twinkle and smears fine details. To sharpen their view, astronomers had to develop ingenious techniques. In the 1990s, two teams of researchers, one in Europe and one in the United States, began pioneering methods to overcome the blur. They first employed speckle imaging, taking many rapid-fire snapshots of the galactic center and then combining them with clever computer algorithms to counteract the atmospheric distortion. Soon after, powerful adaptive optics systems came online at large observatories like the Very Large Telescope in Chile and the Keck Observatory in Hawaii. These systems measure the atmosphere's blurring in real time and rapidly adjust a flexible mirror to cancel it out, like steadying a wavy funhouse mirror until the reflection becomes clear. With these advances, the once fuzzy central region snapped into focus. Distinct pinpoints of light materialized out of the haze, each one a star now visible and trackable night after night. What had been an amorphous glow turned into a bustling starfield deep in the galactic core. Thus began a long, patient watch. Astronomers started charting the movements of these central stars with unwavering dedication. Year after year, using the improved infrared vision, they measured each star's position and noted how it shifted. Each star moved only slightly from one year to the next, but over time, those tiny shifts accumulated. It was as if we were watching a colossal celestial carousel in slow motion, each star tracing a graceful arc around an unseen center. By carefully connecting the dots of each star's changing position, the astronomers could map out the paths the stars were following. Points of light that once seemed randomly scattered revealed themselves as members of a vast dance. Over more than a decade, distinct orbits emerged from the data. What had once been mere specks of light on old photographs now became actors on a cosmic stage, each in motion. The stars were effectively serving as test particles, natural probes of the gravitational field deep in the galactic nucleus. Like dry leaves caught in a swirling eddy of wind, their motions betrayed the presence of an otherwise invisible force at the center, guiding them along their paths. Before long, it became evident that all these stellar paths were pointing to one and the same central location. Each orbit, when plotted, turned out to be an ellipse with a common focus, the same mysterious spot at the center of the Milky Way. Just as the planets in our solar system all orbit the Sun, these stars all appeared to be orbiting an unseen object at that central point. What could possibly sit at that location, exerting such a powerful gravitational pull, yet emitting no visible light of its own? The data hinted at something truly extraordinary, an enormous mass confined within a tiny volume of space. This was unlike anything astronomers had encountered elsewhere in the galaxy. All evidence seemed to implicate a supermassive black hole, an object so dense that not even light can escape it. Skepticism gradually gave way to conviction as the stellar data piled up. Among the whirling entourage of stars, one in particular seized astronomers' attention. Later designated S2, or sometimes S0-2 by one research group, this star was observed to complete a full circuit around the invisible center in only about 16 years. In cosmic terms, and compared to any other known star's motions, that is an incredibly short period to orbit such a central point. S2's quick, tight loop meant that it ventured astonishingly close to whatever massive object lies at the core. Its existence and behavior became the cornerstone of the case for the Milky Way's hidden central mass. As the researchers followed S2 through the years, seeing it swing in and then race outward again, they realized they had front-row seats to an unprecedented cosmic experiment. The stage was set to measure the mass and size of the invisible giant that ruled the galactic center, using the orbits of S2 and its companion stars as our guides. For our distant vantage point on Earth, these changes in S2's motion are subtle and require painstaking measurement. But if you could somehow teleport much closer, say to a distance only a few light years from the galactic center, you would witness a breathtaking celestial ballet. Stars like S2 would streak through the sky, moving noticeably over the course of years or even months. At closest approach, S2 would race past in a blur of blue-white light, its brilliance intensified and its color skewed by its immense velocity. You might see its starlight redden as it recedes, literally drained of energy by climbing out of the black hole's gravity, a relativistic effect, imperceptible to the naked eye, but very real to precision instruments. The very fabric of space around you would be curved. Light from background stars might appear bent into arcs, or even smeared into multiple images as it grazes the unseen mass. It would be a front-row seat to Einstein's gravity in action, a scene of whirling stars and distorted light, all centered on an apparently empty patch of darkness where the black hole lurks. We cannot physically be there to behold it with human eyes, but through the eyes of our telescopes and the calculations of physics, we have reconstructed this awesome vision. S2's orbit turned out to be highly elongated, much like the path of a comet swinging around the Sun. This star swoops in toward the galactic center and then swings far back out, following a steeply oval trajectory. At its closest approach, S2 comes within about 120 astronomical units of the center, roughly 4 times the distance of Neptune's orbit from the Sun. In cosmic terms, that is an incredibly small radius to circle such a tremendous mass. Then S2 spends most of its 16-year orbit looping far outward, only to be pulled in again by the center's gravity. It completes this entire circuit in a mere 16 years. By comparison, our Sun takes over 200 million years to revolve once around the Milky Way, and even Neptune takes 165 years to go around the Sun. S2's speedy trip around the galactic center, just a decade and a half, was astonishing to astronomers, clear evidence that the central gravity is immensely strong. As S2 neared its closest point, which it did in 2002 and again in 2018, it accelerated to breathtaking speeds. At pericenter, the nearest approach, S2 was racing at over 5,000 kilometers per second, roughly 2% of the speed of light. That's more than 25 million kilometers per hour. For a moment, it became one of the fastest moving stars ever observed. After whipping around the unseen focus of its orbit, it shot back out, slowing down as it climbed away. Watching such a dramatic acceleration and deceleration was like witnessing a star perform a gravitational slingshot around an invisible sun. This extreme motion offered a direct test of how gravity works in such intense conditions. These precise observations of S2's motion allowed astronomers to calculate exactly how much mass must be lurking at the center to keep S2 on its tight leash. Using Kepler's laws of orbital motion, the same laws we use to compute the mass of the Sun from Earth's orbit, for instance, they plugged in S2's 16-year period and the size of its orbit. The answer was staggering. The central object had a mass on the order of 4 million suns. Nothing less could tug so hard on a star moving so quickly. And remarkably, all that mass had to fit inside S2's small orbital radius of 120 astronomical units. To put that in perspective, 4 million stars like our Sun would normally occupy a region far larger than our solar system. Yet whatever S2 is orbiting confines that mass into a space only a few light days across. Essentially, S2's existence and orbit sealed the case. By the mid-2000s, the evidence strongly indicated a supermassive black hole as the only plausible occupant of the galactic center. One by one, the dancing stars at the galactic center delivered measurements of the invisible mass. S2 was the crown jewel, completing a full orbit by 2002 and providing the first complete set of data for analysis. Other stars, with longer orbits spanning a few decades to centuries, added supporting evidence as their partial arcs were tracked over time. All the stellar orbits pointed to the same central mass and yielded a consistent mass estimate of around 4 times 10 to the 6th solar masses. With each new data point, the numbers became more precise and the conclusion harder to avoid. Something incredibly massive and compact resides at the heart of the Milky Way. S2's rapid whirl around the center became the most compelling evidence yet that a supermassive black hole, or an object every bit as extreme, lies hidden in Sagittarius A star. The once theoretical notion of a black hole at our galaxy's core had moved from speculation to near certainty, supported by hard orbital proof. All these orbital measurements not only pegged the central mass, but also refined our knowledge of the Milky Way's structure. By knowing the exact size and period of S2's orbit, astronomers could calculate our distance to the galactic center itself. The result, roughly 26,000 light-years, agreed with other methods and even improved on them in precision. It is awe-inspiring that by observing a single star's dance, we can map the scale of our entire galaxy and weigh its hidden hub. What once was an educated guess, perhaps a few million solar masses lurk at the core, transformed into a precise figure. Through S2's journey, the paradigm shifted. The Milky Way's dark central mass was no longer a mysterious conjecture, but a measured reality. Even beyond the evidence of mass, S2's journey offered a chance to witness Einstein's relativity in action in the strong gravity regime of a supermassive black hole. Astronomers realized that as S2 swung closest to the center, subtle effects predicted by the general theory of relativity should become detectable in the star's light and motion. In May 2018, when S2 made its long-awaited close approach, or pericenter passage, to the black hole, teams of scientists on high alert pointed their most sensitive instruments at the event. They hoped to catch the faint signatures of warped spacetime, and they succeeded. One key relativistic signal observed was a phenomenon known as gravitational redshift. In essence, as S2 dove deep into the intense gravitational field near the black hole, the very fabric of spacetime stretched the star's light. Photons leaving S2 had to climb out of the black hole's gravity well, and in doing so, they lost a bit of energy. To astronomers on Earth, the star's spectral lines shifted toward the red end of the spectrum, lower energy, compared to where they would be in a weaker gravitational field. This was not due to ordinary Doppler motion, which had been accounted for, but to gravity itself affecting the light, exactly as Einstein's theory had predicted a century earlier. It's as if the starlight was drained slightly of its vigor by the time it escaped the grip of the massive object. The detection was clear. During S2's closest approach, its light became measurably redder in a way that Newton's gravity alone could not explain. It was the first time such a gravitational redshift was seen for a star orbiting a supermassive black hole. Einstein's prediction, made over 100 years ago for how light should behave near a strong gravitational source, was confirmed in dramatic fashion, right in our galactic backyard. In a thought experiment, one might imagine riding along with S2 during its closest approach. As you skim past the black hole at a few percent of light speed, time itself would run differently. An onboard clock would tick a bit slower compared to clocks far away. You would also see strange optical effects. Background stars behind the black hole might appear smeared into arcs, or even multiple images due to the black hole's intense bending of light. It would be a surreal ride, but entirely consistent with Einstein's depiction of gravity. These are precisely the kinds of effects astronomers sought to measure from Earth, using S2's experience as a test of relativity. As S2 continued along its orbit and began to swing away after perihelion, astronomers kept tracking its position with extraordinary precision. In the months and years following the 2018 close pass, they noticed something subtle but profound. S2 was not returning to the exact same path it had before. The orbit had shifted slightly. The ellipse itself was rotating around the black hole. Each time S2 goes through a full circuit, the point of its closest approach advances, making a rosette-like pattern over many orbits. This effect is known as relativistic orbital precession. The amount of S2's precession per orbit turned out to be small, only a few arc minutes, or a fraction of a degree. But it was in excellent agreement with the value predicted by general relativity for a body moving in the spacetime of a 4 million solar mass black hole. A similar kind of precession had been long observed in Mercury's orbit around the Sun, where it is only a tiny 43 arc seconds per century. And that historical puzzle was one of the original proofs of general relativity. Now, with S2, the same phenomenon was observed in a far stronger gravitational context, roughly 10,000 times the curvature of spacetime that Mercury experiences. And once again, Einstein's theory was vindicated. These measurements, gravitational redshift and orbital precession, were landmark tests of gravity in an extreme environment. They dramatically extended the range over which general relativity has been verified, from our solar system to the tumultuous core of the Milky Way. When the analysis was complete, the agreement between observation and theory was almost uncanny. Astronomers were delighted. A century after Einstein formulated general relativity, its predictions were being confirmed in an arena he could only dream of. The success of the S2 experiments not only reinforced our confidence that Sagittarius A star is indeed a black hole, but also showed that the underlying theory of gravity remains rock solid even at the brink of a black hole's domain. It was a proud and thrilling moment in modern astronomy. The Milky Way's dark heart had provided a resounding yes to Einstein's equations. Beyond the satisfaction of weighing the black hole, these observations offered something equally profound: the ability to use the galactic center as a laboratory for fundamental physics. We have, in effect, a naturally occurring experiment where we can watch how space and time behave in the vicinity of a supermassive black hole. With S2's orbit, nature allowed us to test general relativity in conditions far more extreme than any we can create on Earth. And relativity passed the test with flying colours. It is hard to overstate what a leap this represents, moving from the hypothetical musings of a few decades ago to actually measuring the warping of space-time around our galaxy's central black hole. By the late 2000s, the case for a supermassive black hole at the galactic centre had become overwhelmingly convincing. The orbits of stars like S2 provided a firm measurement of the central mass, about 4 million suns, and those orbits also indicated that this mass must be confined to an extraordinarily small region. But could anything other than a black hole account for such a situation? Astronomers diligently considered and ruled out all conceivable alternatives. If not a single massive black hole, one might imagine a cluster of many smaller objects packed into the same volume. Perhaps a swarm of neutron stars, white dwarfs, or stellar mass black holes could huddle unseen at the center, or a dense conglomeration of dark matter particles. However, all these scenarios ran into severe problems when confronted with the data. First, the central mass concentration is astonishingly compact. S2's closest approach of 120 astronomical units, about 17 light-hours, puts an upper limit on the radius of the central object. It must fit entirely within that distance. Otherwise, S2's orbit would have been disrupted or would deviate from a perfect ellipse. 4 million solar masses inside a sphere of 120 astronomical units implies an average density millions of times higher than even the core of a dense star cluster. If one tried to build a cluster of normal stars to equal 4 million suns in that space, the cluster would not remain dark. It would shine brightly from the combined light of so many stars and likely be observable, yet we see no such glow. Moreover, the gravitational interactions in such an ultra-dense cluster would be catastrophic. Stars and stellar remnants would constantly collide or merge, or their close encounters would fling them out of the core in short order. Calculations show that any cluster of massive objects that compact would gravitationally self-destruct on timescales far shorter than the age of the galaxy. In effect, it would either collapse into a single black hole or disperse itself. Either way, it couldn't remain stable as a cluster for long. Could it be a clump of exotic dark matter, or some unknown massive object? This, too, seems highly unlikely. The nature of the central mass had to be consistent with the lack of light and the stability of the stellar orbits. If it were a ball of hypothetical dark matter particles, for instance, it would need to be extraordinarily concentrated, and no known dark matter theory predicts such a sharp concentration at the center. If it were a supermassive star, or any other single object made of normal matter, it should have collapsed under its own weight by now. A star of millions of solar masses cannot support itself. It would either blow itself apart or implode into a black hole. In short, every traditional or exotic alternative ends up either contradicting observations or inevitably turning into a black hole under those extreme conditions. Even speculative entities, like a hypothetical boson star, a clump of exotic particles, or a traversable wormhole, fail to fit the precise data. They would require unknown physics and still wouldn't neatly explain all the clues we have. Another important clue came from radio observations of the mysterious source Sagittarius A star. This compact radio source, sitting at the very center of the stellar orbits, was found to be incredibly small in extent. High-resolution, very long baseline interferometry, VLBI, at millimeter wavelengths, revealed that whatever is emitting the radio waves is confined to a region on the order of just tens of microarc seconds across. That corresponds to a size of only a few tens of light-hours at the galactic center, comparable to the scale of S2's perihelion distance. Such tight limits on the size of Sagittarius A star's emission region further argue that the central mass must be a single, compact object. Combining this size constraint with the huge mass leads to an inevitable conclusion. The central object has a density beyond that of any normal matter configuration, leaving a black hole as the only real candidate. All these lines of evidence, the immense mass, the tiny volume, the lack of any detectable cluster of stars or other emitters, and the extreme compactness of the radio source, converged on one conclusion. By around 2008, astronomers were declaring that the central mass concentration must be a supermassive black hole beyond any reasonable doubt. One of the lead researchers described it plainly as beyond a reasonable doubt in scientific terms. In a practical sense, virtually all uncertainty had evaporated. The Milky Way's center harbors the very kind of object that had been conjectured in other galaxies, a dark behemoth in its core. Our galaxy's hidden heart was no longer a mere hypothesis. It was a real black hole, as concrete as any celestial object we know, albeit one we perceive only indirectly. In hindsight, this discovery aligned with broader findings in astronomy. Many, if not most, galaxies appear to host central black holes, and the Milky Way proved to be no exception. But there is something uniquely satisfying about having detected and measured the black hole in our own backyard. What was once an extraordinary idea had become an accepted fact. A giant black hole sits quietly at the center of the Milky Way, the unseen anchor around which our entire galaxy revolves. The name Sagittarius A star, pronounced Sagittarius A star, had entered the astronomical lexicon decades before the stellar orbits conclusively pointed to a black hole. Back in 1974, two astronomers, Bruce Ballack and Robert Brown, using the Green Bank radio telescope, discovered a compact, bright radio source at the very center of the Milky Way, in the direction of Sagittarius. This source was unlike the diffuse radio glow of gas and supernova remnants in the region. It was point-like and extremely concentrated at what seemed to be the exact middle of the galaxy. Brown added the asterisk to the name Sagittarius A as a playful way to denote its excitement and uniqueness. In atomic physics, an excited state is marked with an asterisk. For years, Sagittarius A was an enigma, a powerful radio beacon emanating from a region no larger than our solar system, with no obvious counterpart in visible light. Many suspected that this might be the signature of a central black hole, but the evidence was not yet ironclad. By the late 1990s and early 2000s, as astronomers mapped the orbits of stars like S2, it became clear that those stars were circling around this very radio source, Sagittarius A star. The invisible mass deduced from the stellar motions coincided with the position of Sagittarius A star to within a tiny margin. In other words, the mysterious radio source was sitting right at the focus of all the stellar orbits, exactly where the gravitational center had to be. This was a crucial piece of the puzzle. It tied the phenomenon of the star's rapid orbits to a physical object that could be studied with other tools. Sagittarius. A star effectively became the face of the Milky Way's central black hole. Not a face in visible light, to be sure, but a location on the sky from which we receive telltale signals. Sagittarius. A star is most conspicuous in radio waves. At wavelengths of a few centimeters to a few millimeters, it shines with a steady, if modest, flux. To put it in perspective, if we could see radio waves, the galactic center would appear as a gentle glow with Sagittarius, a star as a slightly brighter dot at the core. In optical light, however, Sagittarius A star is invisible, hidden both by dust and by its intrinsic faintness. Even in high-energy X-rays, Sagittarius. A star is usually very dim. Only during occasional flares does it light up enough to be prominent, which we will discuss later. This relative faintness is itself a clue. It indicates that, unlike the voracious black holes in active galactic nuclei, quasars, that blaze brightly, our black hole is currently starved and quiet. Most of the time, Sagittarius A emits only as much energy as a few thousand suns, an extremely meager output for a 4 million solar mass object. Yet, even though it is faint, Sagittarius, a star, is undeniably present and sometimes shows flickers of activity. Astronomers monitoring it over the years noticed that it varies slightly from day to day at radio and infrared wavelengths. In May 2019, observers witnessed it flare in the infrared to an unprecedented brightness, the brightest burst ever seen from Sagittarius A star. Such an outburst likely meant a blob of extra material, perhaps debris from a shredded star or a gas cloud, had suddenly been swallowed, giving the black hole a momentary surge of activity. These occasional fireworks remind us that while usually subdued, Sagittarius A star can awaken briefly when fed. Every so often, it produces a burst of radiation, sudden flares, especially in the infrared and X-ray bands. We will delve into those shortly. These flickers and flares are like the heartbeat or pulse of the black hole, a reminder that there is an accreting object there that can get feisty on occasion. Critically, Sagittarius. A star does not wander on the sky. It stays essentially fixed at the center, reinforcing that it is extremely massive and dominates the gravity of its neighborhood. Precise measurements of its position over years have shown virtually no motion relative to the background stars. That is exactly what one would expect for an object that outweighs any other single mass in the region. It's the anchor of the system. If the radio source were, say, a cluster of smaller objects, we might see it jiggle or spread out over time. Instead, Sagittarius, a star, remains compact and stationary to within just a few kilometers per second, essentially serving as the dynamical center of the galactic center. It's the stationary hub around which the stars orbit. The recognition that Sagittarius A star is the Milky Way's central black hole has been profound for astronomy. It gave us a concrete target for detailed study, a single identifiable source that we can point our instruments at and say, there lies the black hole. In the decades since its discovery, Sagittarius A star has been probed across the electromagnetic spectrum and has served as a proving ground for theories of black hole accretion and strong gravity. What was once a speculative radio oddity has now been firmly established as the very heart of our galaxy, the embodiment of our supermassive black hole, quietly lurking at the center and communicating its presence through radio waves and the motions of the stars that surround it. Yet one compelling piece of the puzzle remained. Could we ever actually see the immediate vicinity of the black hole itself? By its nature, a black hole emits no light from within its event horizon, but astronomers hope to capture its silhouette, the shadow it casts against the glowing material around it. If we could take a picture sharp enough, the black hole's outline might be observed as a dark spot surrounded by a ring of light. Achieving this, however, required resolving an incredibly small feature on the sky. The predicted size of the shadow of a 4 million solar mass black hole at 26,000 light-years away is on the order of 50 microarcseconds. That is equivalent to trying to see an object the size of a tennis ball on the moon, an almost inconceivable level of angular resolution. No single telescope on Earth comes anywhere close to that degree of detail. The solution to this daunting challenge emerged from the technique of very long baseline interferometry, VLBI. By linking together radio telescopes across the globe and having them observe in unison, astronomers can effectively create a planet-sized telescope. In the mid-2000s, a project called the Event Horizon Telescope, EHT, took shape. A worldwide collaboration harnessing telescopes from Hawaii to Arizona, from Mexico to Spain, from Chile to the South Pole. Each telescope in the network recorded the faint radio waves coming from Sagittarius A star at a wavelength of about 1.3 millimeters, the submillimeter band, during coordinated observing sessions. Atomic clocks at each site time-stamped the data to synchronize the observations down to the billionth of a second. Later, massive computing facilities would combine these recordings, using the interference patterns of the radio waves to reconstruct an image with extremely high resolution. It was an audacious endeavor that pushed technology and coordination to their limits. Essentially, astronomers were using the Earth itself as one giant telescope mirror. Early test observations with this VLBI network gave encouraging hints that the technique could work. In April 2017, the EHT conducted a major observing campaign. Across continents, multiple dishes all turned toward the same targets. The supermassive black hole in the galaxy M87, much larger and more distant than ours and Sagittarius A star. The data from all those telescopes, literally petabytes of hard drive recordings, were flown to central processing centers, where they were painstakingly correlated. One can imagine the scene. At observatories around the world, teams of astronomers worked through those nights, training their radio dishes on the invisible center of the Milky Way. On Mauna Kea in Hawaii, evening was just beginning, as, at that very moment, dawn was breaking over the Chilean Andes, and midday sun hung in the sky at the South Pole. Despite differences in locale and time, each telescope's instruments kept perfect time with their atomic clocks, collecting wave after wave of radio signals from Sagittarius A star. Hard drives filled with data. When the observing run was over, these drives were shipped and combined at correlation centers. It was a truly global enterprise, humanity coming together to sharpen its vision to the necessary acuity of tens of microarcseconds. In the end, all that effort and coordination paid off magnificently. In April 2019, the EHT team unveiled a result that made headlines worldwide. The first ever direct image of a black hole's immediate surroundings. It was the now famous photograph of a lopsided ring of orange light encircling darkness at the core of galaxy M87, the shadow of that galaxy's monstrous black hole. This stunning confirmation showed that it was indeed possible to image something right at the brink of a black hole's event horizon. Buoyed by that success, the team pressed on to extract an image of our own galactic center's black hole. Imaging Sagittarius. A star proved more challenging than imaging M87's black hole for a couple of reasons. First, Sagittarius. A star is much smaller in physical size. Despite its millions of solar masses, it is thousands of times less massive than M87's black hole, which means the material orbiting around it does so much faster. The hot gas around Sagittarius A star can change on timescales of mere minutes. During a single night of observing, the brightness pattern literally evolves. This made it tricky to produce a clear time-averaged image, a bit like trying to photograph a fast-moving subject with a long exposure. Second, the line of sight to the galactic center passes through turbulent interstellar material that scatters and blurs the radio waves slightly. Nevertheless, after refining their algorithms to account for these complications, the EHT team was able to reconstruct an image of Sagittarius A star as well. In May 2022, they announced the result: a faint, donut-shaped ring of emission with a dark interior, about 50 microarcseconds across, exactly the size anticipated by theory and earlier mass measurements. We were, in essence, gazing at the shadow of the black hole. This image of Sagittarius, a star, was a breathtaking milestone. It marked the first time humanity has seen the immediate vicinity of our own galaxy's central black hole. In the picture, the darkness in the middle is not the physical object. The event horizon itself is a bit smaller than the shadow, but rather the imprint of its gravity on the surrounding light. The glowing ring arises from radio-emitting plasma circling just outside the event horizon, its light bent and magnified into a halo by the tremendous gravity. The fact that we observe a ring of roughly the expected diameter is yet another affirmation that we are indeed looking at a black hole, and that general relativity correctly describes its behavior even at the threshold of the abyss. This achievement truly captured the shadow's edge, the boundary between the visible universe and the unknowable interior of a black hole, and turned a theoretical concept into a tangible, observed reality. Even though the EHT images are somewhat fuzzy, they carry a profound message. We have effectively seen the unseeable. With continued improvements, more telescopes added to the array, more sophisticated imaging algorithms, future observations will likely sharpen the picture of Sagittarius A star, and perhaps even allow us to discern details such as the orientation of the black hole's spin or the pattern of magnetic fields threading the plasma. For now, the successful imaging of the black hole's shadow stands as a triumph of human ingenuity, a direct visual confirmation of the hidden heart of the Milky Way, captured by linking telescopes across our planet and turning our gaze toward the ultimate dark center. Not only can we now image the black hole's vicinity, we can also watch matter dancing just outside its grasp in real time. Astronomers have observed that Sagittarius A star, usually so quiet, will occasionally erupt in a brief flare of energy. In the early 2000s, this discovery was a revelation. In 2001, the Chandra X-ray Observatory caught an unexpected burst of X-rays from the galactic center. Sagittarius, a star, had brightened by a factor of nearly 100 for an hour before fading again. Shortly thereafter, infrared telescopes also detected flickers of brightness from the black hole's location. These flares were the first direct evidence that material around the black hole sometimes gets heated and accelerated dramatically, causing a sudden flash of radiation. Normally, Sagittarius A star is faint, but during a flare it becomes momentarily thousands of times more luminous in X-rays and infrared. Careful monitoring has shown that such flares occur, on average, a few times per day in the infrared, and roughly daily in X-rays, though most are relatively small. When a significant flare happens, the region around the black hole lights up for an hour or so, then returns to its quiescent state. Astronomers liken these events to solar flares, bursts of energy powered by magnetic reconnection, albeit on a far more extreme scale. A remarkable aspect of these flares is that the light is often highly polarized. In other words, the waves of infrared light from a flare tend to vibrate preferentially in a certain direction, a telltale sign that they originate from electrons spiraling around magnetic field lines, synchrotron emission. During some flares, the polarization angle has been observed to swing steadily, almost as if we are tracking the motion of the emitting source. Indeed, mounting evidence suggests that many flares are caused by hotspots, blobs of plasma heated to enormous temperatures and orbiting very close to the black hole. As a blob moves around, one side of its emission appears slightly brighter due to its motion toward us boosting the light via Doppler effect, and then fainter as it swings around to the far side. This behavior, along with the rotating polarization angle, is exactly what we'd expect from a compact clump of material zipping around the black hole. In 2018, astronomers using a cutting-edge instrument called Gravity, an infrared interferometer on the Very Large Telescope, were fortunate to witness a series of strong flares shortly after S2's close pass. During those observations, they could actually track the position of the infrared emission centroid as the flare unfolded. Remarkably, it moved in a loop, indicating that the flare was coming from a blob of gas revolving around the black hole. The inferred orbital period was on the order of 45 minutes. To put this in perspective, an object orbiting in 45 minutes must be only a handful of Schwarzschild radii from the black hole's event horizon, moving at a substantial fraction of light speed. Sure enough, calculations suggested the hotspot was orbiting at about 30% of the speed of light, at roughly 5 to 10 times the Schwarzschild radius, practically skimming just outside the horizon. Around and around it went, like a planet on fast forward, except gravity was so strong that space and time themselves were being twisted by the black hole's rotation. Around the same time, complementary evidence came from radio observations. Using ALMA, a powerful radio array in Chile, in tandem with the global EHT network, astronomers detected clues of a hotspot emitting at sub-millimeter wavelengths. In those data, a flare showed signs of an orbiting blob with a roughly 70-minute period. Interestingly, modelling of that flare suggested that we might be viewing the orbital plane nearly face-on. The hotspot appeared to move in a clockwise loop on the sky with little up and down motion. This aligns with the idea that our line of sight to the accretion disk of Sagittarius A star is almost along the black hole's pole, though more data are needed to confirm the precise geometry. Watching these flares in real time provides an unprecedented window into the black hole's immediate environment. Through these sudden illuminations, astronomers are effectively witnessing matter in its final dance around the black hole before crossing the point of no return. As a plasma blob orbits, its light output rises and falls, and its polarization swings, offering rich information about conditions in that extreme region. The fact that we see such rapid orbits, some matter circling in mere tens of minutes, is breathtaking. These observations confirm that gravity just outside the event horizon is behaving as general relativity predicts, and they even hint at the orientation of the black hole's accretion disk, and possibly its spin. Each flare is a brief beacon from the brink of the abyss, illuminating the physics of plasma, magnetic fields, and gravity in one of the harshest environments in the galaxy. What causes the flares? The prevailing thought is that tangled magnetic fields in the accretion flow occasionally undergo a violent reconfiguration, akin to the magnetic reconnection that triggers solar flares on the Sun. When this happens near a black hole, a pocket of plasma gets suddenly heated and accelerated, emitting a burst of radiation. In essence, the black hole's magnetized ring of gas periodically crackles with these little storms, and we see the flash of light they produce. After the flare subsides, the hot spot likely shears apart or plunges inward, and the black hole's vicinity returns to its quieter state. By studying flares, scientists are learning about the magnetic properties and particle energies in the accretion flow, information that is otherwise very hard to come by. In the coming years, continued monitoring of Sagittarius A star's variability with instruments like gravity, ALMA, and future observatories will further flesh out this picture. We may catch flares from different viewing angles or identify patterns in their frequency and intensity. Already, these hotspot observations are providing hints about the black hole's spin and the orientation of its rotation axis, since the direction and tilt of the orbits we observe depend on how the disk is oriented relative to us. While not yet definitive, such clues are tantalizing. The flares and hotspots are effectively nature's own test particles, zipping through the black hole's gravitational field and allowing us to watch relativity unfold on timescales of minutes. It's a truly mesmerizing cosmic light show, one happening 26,000 light-years away. Yet by tracking it, we extend our senses right into the domain of strong gravity. Under normal circumstances, the black hole at our galaxy's center is remarkably quiet, almost inconspicuous in terms of energy output. Despite its colossal mass, Sagittarius A star radiates only a feeble trickle of radiation. It's as if this cosmic giant is on a starvation diet. Astronomers describe the black hole's mode of feeding as a radiatively inefficient accretion flow. In simpler terms, that means the gas falling toward the black hole isn't converting much of its gravitational energy into light. Instead of forming a brilliant flat disk and glowing fiercely, as happens in quasars, most of the infalling material around Sag A star stays hot and dilute, and much of its energy remains locked in thermal motion or carried off by outflows, rather than being efficiently radiated away. Why would a black hole devour matter so inefficiently? The environment near Sagittarius, a star, provides some clues. The gas supply trickling inward comes from the winds of young massive stars scattered within a few light-years of the center. Dozens of these hot, bright stars blow strong stellar winds, and some fraction of that gas finds its way toward the black hole. However, the amount of gas is relatively small, and it's very tenuous. As this gas nears the black hole, it becomes extremely hot, tens of millions of degrees, and ionized. In such a thin, superheated plasma, the atoms and electrons hardly collide. They are too far apart, so they don't radiate away their energy efficiently before plunging inward. The result is an accretion flow that is puffed up and nearly spherical, more like a slowly inward drifting cloud or fog than a thin, shining disk. Because the particles don't efficiently shed their energy as light, they don't cool and settle. Instead, they stay in random, hot motion. In fact, a lot of the gas may actually escape. Theoretical models predict that much of the infalling matter gets blown away by the heat and pressure of the flow itself, or remains in orbit rather than falling straight in. Only a trickle of the available material actually reaches the event horizon. The observable signature of this starving accretion mode is a distinctive spectrum. Sagittarius. A star emits most strongly in radio and millimeter wavelengths. At those long wavelengths, it has a fairly flat or rising spectrum, meaning the emission grows brighter toward the submillimeter band. There is a notable bump in the spectrum around a few hundred gigahertz, the submillimeter bump, corresponding to wavelengths of about 1 millimeter. This bump represents the peak of the emission from the innermost region of the flow, essentially the glow of hot electrons in the magnetized plasma near the black hole. At frequencies higher than the submillimeter, into infrared and X-rays, the quiescent emission from Sag A star drops off steeply. In fact, under normal conditions, the black hole is effectively invisible in optical or X-ray light. Any would-be signal is either too faint to notice or absorbed by intervening dust. Only during flares does it briefly light up at those energies. So, unlike a luminous quasar that can be seen across the universe, our black hole is practically dark, except for its gentle radio whisper and the occasional flicker of higher energy light. From an energy standpoint, Sagittarius. A star is astonishingly underluminous. If one computes the theoretical maximum power it could radiate, known as the Eddington luminosity, where radiation pressure would balance gravity's pull, a 4 million solar mass black hole could, in principle, shine with the light of about 10 to the 11th suns. In reality, Sag-A outputs only about 10 to the power of 3 suns worth of radiation or less, meaning it's radiating at only about 1/10,000,000th of its Eddington limit. Put differently, the black hole is using an infinitesimal fraction of its horsepower. This inefficiency is a hallmark of the RIAF, radiatively inefficient accretion flow, regime, and tells us that most of the gravitational energy of infalling gas is not being turned into light. Instead, it likely stays as heat in the gas, or is carried off by winds and possibly weak jets. Indeed, astronomers have looked for jets from Sagittarius A star. Many accreting black holes, especially those that are underfed, produce narrow jets of high-speed particles that shoot out along the rotation axis. In Sag-A's case, any jet is extremely feeble, a testament to how little energy is being channeled into such collimated outflows. There have been hints of a small radio jet or outflow stretching a few light years from the galactic center, but nothing like the spectacular jets observed in galaxies like M87. If a weak jet does exist, it's barely sputtering and easily lost in the surrounding radio emission. Most of the energy instead seems to dissipate in the hot plasma or escape as a more diffuse wind. Studying this dim accretion flow has been challenging, but it has yielded important insights. The spectrum and polarization of Sag-A star's radio emission. The radio waves are slightly polarized, indicating organized magnetic fields, have been used to constrain the density and temperature of the plasma. By fitting detailed RIAF models to the observed sub-mm bump and overall radio output, scientists infer that the density of electrons in the innermost region is low and their temperature is extremely high, on the order of 10 to the 11th to 10 to the 12th Kelvin. These models also suggest that the accretion rate onto the black hole, the amount of mass actually crossing into it, is minuscule, perhaps only a few times 10 to the -9 solar masses per year. For comparison, that's only a few billion kilograms per second, which sounds like a lot, but for a black hole of this size is practically nothing. Most of the gas that starts falling in never reaches the black hole. It either gets heated and blown away, or remains orbiting at a safe distance. Sagittarius. A star thus offers us a close-up example of a black hole sipping, not gulping, its food. It confirms that not all supermassive black holes are ravenous engines lighting up their galaxies. Ours is a case in point. A giant black hole that is currently quiescent, perhaps because it lacks a steady fuel supply, or because feedback from the hot accretion flow itself keeps fresh gas from cooling and falling in. Interestingly, there is evidence that our black hole has not always been this quiescent. Structures like the Fermi bubbles, huge gamma-ray emitting, lobes extending north and south of the galactic center, suggest that a few million years ago, Sagittarius A star may have undergone a period of much more vigorous activity. At present, however, it slumbers in a low-power state. For life on Earth and elsewhere in the Milky Way, this is perhaps fortunate. A violently active galactic nucleus can flood a galaxy with intense radiation and high-energy particles. The Milky Way's black hole, in its subdued mode, is a benign presence. It's quietly doing its part in the galactic ecosystem, heating the central region just a little, stirring the pot of gas and dust, but not blasting us with any devastating energy. In a sense, we live in a galaxy with a tame dragon at its core, massive and potentially fearsome, but currently dozing. For scientists, this presents an excellent opportunity. We can study the physics of accretion in a relatively clean and calm setting, without the overwhelming glare of a quasar to blind our instruments. Each insight gleaned from Sagittarius, a star's faint emissions, helps us understand the full range of behaviors black holes can exhibit, from the most furious quasars to the most quiescent galactic nuclei. Over the past few decades, the galactic center has truly become a precision laboratory for testing the laws of gravity. What was once a region of mere conjecture is now providing some of the most stringent examinations of Einstein's general relativity ever conducted. It's as though nature kindly placed a giant black hole in our cosmic backyard and said, "Here, use this to probe gravity's limits." And astronomers have been doing exactly that. One of the key triumphs already achieved was the confirmation that Einstein's theory holds up under the strong gravitational conditions near Sagittarius as star. The gravitational redshift observed in S2's light and the orbital precession measured in its path were textbook tests that general relativity passed with flying colours. These measurements dramatically extended the range, both in gravitational field strength and distance scale, over which general relativity has been verified. In our solar system, we had tested relativity with phenomena like Mercury's orbit and gravitational redshift in Earth's field. But the galactic center tests are on an entirely different scale, a regime of much stronger gravity and higher orbital speeds. So far, every observation near the Milky Way's black hole has been consistent with Einstein's predictions. There is no sign of Newton's laws breaking down, nor any exotic new physics required, even in this region of intense gravity just outside a supermassive black hole. Naturally, astronomers are keen to push these tests even further. The experiments to date, tracking S2 and a handful of other stars, probe what could be called the moderate gravity regime around the black hole, still far from the event horizon, but much stronger than anything in the solar system. To explore the truly extreme predictions of general relativity, researchers are hunting for stars or other objects that venture even closer to the black hole. If a star with an orbital period of just a few years, or even months, could be identified, it would approach so near the black hole that relativistic effects like frame dragging, the twisting of spacetime by the black hole's rotation, might become detectable in its orbit. Such a star would be influenced not just by the black hole's mass, but also by its spin, offering a way to measure that spin via the subtle gravitomagnetic tug on the star's motion. Encouragingly, hints of such stars are beginning to emerge. In recent years, observations have suggested the presence of several faint S-stars inside S2's orbit, candidates with shorter periods. One star, sometimes referred to as S62, is thought to have an orbit of around 10 years, bringing it even closer to the black hole than S2 does at its nearest approach. If confirmed, S62 and others like it will allow even more stringent tests of gravitational physics in the near future. Each of these stars is like a new probe dropped deeper into the black hole's potential well. Another thrilling prospect is the discovery of a pulsar in a tight orbit around Sagittarius A star. Pulsars are spinning neutron stars that emit beams of radio waves with clock-like regularity. They are phenomenal tools for precision measurements because their pulses can be timed to fractions of a millisecond. If one were found orbiting the black hole, it would be like having an exquisitely precise clock moving through the black hole's space-time, ticking off the effects of gravity. Such a system could allow measurements of phenomena like the black hole's frame dragging and even tests of the no-hair theorem, which states that a black hole is fully described by only its mass and spin. Scientists have been conducting deep radio surveys of the galactic center for exactly this reason. In 2013, one pulsar was indeed discovered relatively close, a magnetar, highly magnetized pulsar, about 0.1 parsec from Sagittarius A star. While that one is too distant to probe the strongest gravity, its detection raises hope that others may lurk nearer in. The galactic center is a crowded and messy environment for radio waves, but new techniques and more sensitive telescopes might eventually pluck out the telltale ticking signal of the right kind of neutron star orbiting in just the right place. Meanwhile, instrumentation on Earth is rapidly advancing. The next generation of giant telescopes is poised to sharpen our view of the galactic center even further. For example, the Extremely Large Telescope, ELT, under construction in Chile, will have a 39-meter mirror and advanced adaptive optics. It is expected to resolve stars at the galactic center roughly 10 times better than current 8 to 10-meter telescopes. Astronomers anticipate that with the ELT, they will discover whole swarms of previously unseen stars, moving even closer to the black hole. These faint, fast-moving stars, perhaps including lower-mass stars that we haven't been able to see yet, could fill in the map of orbits in the central light month of the galaxy. Each additional star would offer another opportunity to check for relativistic deviations, like extra precession of its orbit, slight shifts in its timing, or spectral shifts due to gravitational redshift. By observing how their orbits deviate even minutely from perfect Keplerian ellipses, researchers can detect the subtle fingerprints of relativistic effects or the gravitational influence of any unseen mass, such as a cluster of smaller black holes or dense dark matter near the black hole. Even beyond stars and pulsars, the Event Horizon Telescope's achievements have opened a new avenue for testing gravity right at the black hole's edge. The size and shape of the shadow, captured in the radio images of Sagittarius, a star, can be compared against precise predictions from general relativity. Thus far, the diameter of the observed ring, on the order of 50 microarcseconds, matches extremely well what we expect for a black hole of 4 million solar masses, leaving little room for exotic alternatives, like hypothetical boson stars or other exotic compact objects. As imaging techniques improve, scientists will scrutinize the photon ring for any irregularities that might hint at new physics. If Einstein's theory holds completely, the shadow should remain circular and have a size dictated by the black hole's mass and spin. Any deviation could be a sign of something novel. All these efforts combined make the center of our galaxy a proving ground not just for black hole astrophysics, but for fundamental physics itself. It's quite amazing. A region that for so long was hidden and inaccessible has become one of the best places to test the fabric of spacetime. With each new tool and observation, our backyard, supermassive black hole yields more secrets. The journey is ongoing. As technology pushes boundaries, what was once science fiction, like imaging a black hole's surroundings or watching a star orbit one in real time, is now science fact. The galactic center's transformation from a remote curiosity to a precision laboratory has not gone unnoticed. In 2020, the Nobel Prize in Physics was awarded jointly to Reinhard Genzel and Andrea Ghez, the leaders of the two rival teams that traced the orbits of the central stars, as recognition for the pivotal discovery of our galaxy's supermassive black hole. With all that has been learned, what then do we know for certain about this hidden black hole, and what remains a mystery? The mass of Sagittarius. A star is measured with unparalleled precision, about 4 million times the Sun's mass. Its position at the galactic center is pinpointed to within a fraction of a light year. There is little doubt now that this object is indeed a supermassive black hole. Yet other key properties of the black hole are still not well determined. Chief among these is its spin, the rate at which the black hole itself is rotating. The world took note of this scientific triumph. In 2020, the Nobel Committee honored Genzel and Ghez for providing the most compelling evidence of a supermassive black hole at our galactic center. A fitting acknowledgement of how significant this discovery was to our understanding of the cosmos. General relativity tells us that a rotating black hole can be completely described by its mass and its spin, neglecting electric charge, which is negligible here. While we have the mass in hand, the spin of Sagittarius, a star, remains elusive. Yet spin is a fundamentally important trait. It governs how space-time is dragged around the black hole and can affect whether or not the black hole produces jets or other phenomena. Knowing the spin would also give insight into how the black hole grew over time, since a history of steady, directional accretion tends to spin a black hole up, whereas chaotic, sporadic feeding might leave it with a modest spin. Does it spin rapidly like a cosmic flywheel, or more slowly and sedately? Different studies have offered educated guesses, but no definitive measurement yet. The difficulty is that spin's effects on the orbits of stars, or on the glow of the accretion flow, are very subtle. They might manifest through frame dragging, the twisting of space-time mentioned earlier, or perhaps in the orientation of any jet that might be present. But so far, these clues have been hard to capture. The Event Horizon Telescope's image did not have enough clarity to reveal the spin either. A fast-spinning black hole can in principle cause a slight asymmetry in the emission ring, but the current data for Sagittarius A star were not sufficient to pin this down. Thus, the spin magnitude could be anything from near zero up to a substantial fraction of the maximum allowed, and we simply do not know yet. The orientation of the black hole's spin axis is another question mark. Some indirect evidence suggests that we might be viewing the accretion disk nearly face-on. The looping motions of hotspots observed in infrared and radio flares seem to imply an orbital plane oriented almost head-on to Earth, with the blobs moving clockwise on the sky. If the disk is roughly aligned with the black hole's equator, that would mean the black hole's pole, and any notional jet, is pointing roughly toward our line of sight. However, this interpretation is tentative. Other hints, such as a faint X-ray outflow observed in some studies, or the orientation of certain rotating star disks in the region, have been used to argue that the black hole's axis could be tilted differently. At present, we cannot be certain which way Sagittarius A star is pointing. Beyond spin and orientation, there are broader mysteries too. We still do not fully understand how Sagittarius A star accumulated its mass, whether through steady accretion of gas over billions of years, periodic feasting on captured stars, or mergers with other black holes in the distant past. In fact, there are clues, such as the enormous gamma-ray emitting Fermi bubbles extending above and below the galactic center, that suggest our black hole had periods of quasar-like activity in the past, perhaps a few million years ago. Those might have been triggered by a surge of gas accretion or a merger event. However, the exact growth history of Sag A star remains uncertain. The environment immediately around the black hole also holds unanswered questions. For example, why are there fewer old faint stars near Sagittarius A star than expected? Theory predicted a dense cluster of stellar remnants around a central black hole, but observations haven't found as many as anticipated. It's possible that gravitational interactions have ejected many would-be companions, or that the energetic conditions near the black hole prevent stars from forming or surviving long in its vicinity. This missing cusp of old stars remains an intriguing puzzle in galactic center research. As of now, the Milky Way's central black hole stands as the best studied example of a supermassive black hole anywhere. Yet it keeps some of its secrets close. We know its mass and location intimately, and we have even glimpsed its silhouette and watched the swarming stars that dance to its tune. But characteristics like its spin are still like ghosts in the data, present in theory, but not yet pinned down by observation. Future instruments and experiments will no doubt sharpen our view. Perhaps a lucky discovery of an orbiting pulsar, or even more detailed imaging and spectroscopy, will finally measure the spin and orientation precisely. For astronomers, these remaining unknowns are not disappointments, but rather opportunities. the next set of questions to answer as we continue to probe the heart of our galaxy. Each new breakthrough at the galactic center reaffirms how far we have come, while enticing us with how much more there is to learn. The hidden heart of the Milky Way has been revealed to be a black hole beyond any reasonable doubt. Yet in many ways, we are only beginning to truly know this enigmatic giant. In the years and discoveries to come, we will keep peeling back layers of mystery, inching ever closer to understanding this central dark force that anchors our galaxy, and by extension, gaining insight into the fundamental nature of gravity and extreme physics. In a way, the Milky Way's central black hole has gone from a mere hypothesis to a character we can observe and learn from, a transformation that highlights the power of human curiosity. What was once invisible and unknown is now a source of wonder and knowledge. It's worth noting that our galactic center serves as a template for understanding the centers of other galaxies as well. Supermassive black holes are now believed to reside in most galactic cores, and their masses and spins can influence the evolution of their host galaxies over cosmic time. By studying Sagittarius, a star up close, we gain knowledge that can be applied to far-off galaxies and luminous quasars, shedding light on how black holes grow and how they affect their surroundings. In this way, our Milky Way's black hole is not just an isolated curiosity. It's a key piece in the grand puzzle of how galaxies and black holes co-evolve across the universe. As we continue this cosmic exploration, we deepen not only our understanding of a single black hole, but also our appreciation of the vast and elegant universe it inhabits. The story of Sagittarius. A star is still unfolding, and the next chapters promise to be just as captivating as the last. Yet the black hole does not float in empty solitude. It dwells in a cosmic city center, crowded with stars and gas, a bustling hub hidden in the Milky Way's depths. Countless stars fill this nuclear metropolis, packed so tightly that the space between them seems to shrink. The result is a scene of both brilliance and peril, a place where stellar neighbors race past one another in a chaotic ballet. Here in the galactic core, night never truly falls, for the sky is illuminated by the collective glow of 1,000,000 suns sharing the same cosmic neighborhood. In our corner of the galaxy, the nearest star lies light years away. But in this central hub, stars are crammed into a space so small that dozens could fit within a single light-year cube. Imagine more than 1,000,000 suns crammed into a volume only a few light-years across, a space that, in our neighborhood, would hold only a single star. The density is staggering, far beyond anything our earthly skies could reveal. It turns the core into an astronomical city that never sleeps, every cubic parsec teeming with stellar life. In this tightly packed stellar crowd, each star hurtles along under the black hole's gravitational command. They zip around at tremendous speeds, some traveling thousands of kilometers per second as they whip around the galactic center. It is a cosmic rush hour, akin to a busy city intersection where near misses are routine. Stars pass incredibly close to one another, often skimming by with only a fraction of a light year to spare. And sometimes, in the most congested zones, two stars may even meet in a direct collision, an almost unthinkable occurrence in the quieter galactic suburbs where stars are light years apart. When stars collide in this densely populated neighborhood, the results are dramatic. Two merging stars can coalesce into one larger star, shining as if reborn with newfound youth. Astronomers liken these events to cosmic rebirths, old stars rejuvenated by cannibalizing a neighbor. Other collisions can strip a star of its outer layers, leaving behind a dimmer, exposed core that wanders on like a stellar ghost. These violent encounters alter the stellar population, creating peculiar misfit stars that stand out amid the throng, some appearing unexpectedly young or unusually low in mass for their age. Even without direct collisions, close gravitational encounters can dramatically alter a star's destiny. In a near miss between two stars, one can steal momentum from the other or from a passing binary pair. The result might send one star careening outward at such high speed that it escapes the galactic center entirely, a cosmic exile known as a hypervelocity star. Indeed, astronomers have spotted a few stars traveling so fast they are on track to leave the Milky Way, likely flung from this very region by gravitational slingshots. Thus, for every star that is destroyed or reborn in a collision, another might be cast out, carrying secrets of the central hub to the far reaches of space. Survival in the galactic center is a daunting challenge, even for the hardiest stars. The giants among them, bloated red stars nearing the ends of their lives, often fare poorly in this cosmic mosh pit. Many are missing entirely from the innermost region, suggesting they did not survive the congestion. Perhaps their swollen atmospheres were peeled away by grazing encounters with neighbors, or buffeted by the intense winds and radiation that permeate the region. Some scientists even speculate that in the past, blasts of energy from the supermassive black hole, jets or outflows, might have scoured the inner sanctuary and stripped these giants of their outer layers. Whatever the cause, what remains are the tough survivors. Compact stars, and those nimble enough to endure the gravitational jostling. The more fragile giants have faded or been torn apart over time, leaving a conspicuous absence of old, red beacons in the heart of the galaxy. Any planetary systems that once formed around stars here would face extreme hardship. A planet's orbit could be twisted by the gravity of passing stars, or even stolen away entirely in a close encounter. If one could stand on a planet near the galactic center, somehow shielded from the lethal radiation, the night sky would be awash in starlight. Countless suns would crowd the heavens, many shining as bright as the full moon, or brighter, their hues ranging from cool red embers to hot blue beacons. Dark clouds of cosmic dust would streak the sky as well, blocking some distant light, but the collective radiance of nearby stars would ensure darkness never truly falls. It would be a breathtaking, disorienting vista, beautiful and overwhelming in equal measure. The constellations would be a chaos of brilliance, changing night by night as nearby stars streak across the sky with their rapid motions. One star might outshine Venus one evening, only to swing out of view weeks later as it races through its orbit. The familiar patterns that human stargazers know would be entirely washed out by the constant glow and movement. The very concept of a dark night would lose its meaning amid this perpetual radiance. All the while, harsh ultraviolet and X-ray radiation would pour from massive neighbors, potentially tearing away atmospheres and sterilizing any unlucky worlds. It is as if ordinary planetary life must adapt or perish in this unforgiving district. Only the most tightly bound companions and robust systems stand a chance amid the gravitational turmoil. Yet amid the chaos and hazard, there are sights that defy expectations. Nestled in this turbulent hub are clusters of surprisingly young, massive stars, brilliant blue-white lights that by all rights should have had difficulty being born here. Their presence is a cosmic paradox, an intriguing clue that even in adversity, new life can emerge. These central youthful stars gleam with unexpected vitality, seemingly defying the harsh environment around them. How these stellar youths came to be neighbors of a black hole is one of the central mysteries of this galactic metropolis, leading us deeper into the puzzle of the Milky Way's heart. These young stars orbit the monstrous black hole on paths that often align like a rotating disk, a thin plane of stellar traffic circling the darkness. Dozens of these bright, hefty suns, some tens of times the mass of our sun, live in a loose ring only a few light years from the black hole. They burn hot and blue, flooding the surrounding space with intense ultraviolet light. Seeing such luminous O-type and Wolf-Rayet stars in the black hole's backyard posed a riddle. By our understanding, such stars should be unlikely to form under the black hole's gravitational tyranny. Their existence is often called the paradox of youth, because finding a bevy of young stars so deep in the galaxy's core seemed as surprising as finding a blooming oasis in the middle of a desert. According to conventional wisdom, the tidal forces near a supermassive black hole should tear apart any gas cloud before it can collapse into stars. The black hole's gravitational tides are like cosmic hands, pulling and stretching anything that ventures too close, preventing the calm, dense conditions needed for starbirth. Yet here they are, stellar youths in a place they seemingly do not belong. One possibility is that they were not born there at all. Their story may have begun in calmer waters. Perhaps somehow, 6 million years ago or so, conditions in the center became just right. A colossal gas cloud might have wandered inward, dense and massive enough to resist being shredded by tidal forces. Under the black hole's gaze, that cloud could have flattened into a spinning disk around the center and then fragmented, giving rise to a burst of new stars in spite of the odds. In this scenario, the young stars are children of a once unified giant disk of gas that managed to form stars under extreme conditions. When astronomers first discovered these youthful stars, they were astonished. In a region dominated by ancient stars and the gravitational crush of a black hole, finding hot, blue newborns was akin to discovering blooming flowers on a glacier. These massive stars live fast and die young, usually turning up in rich star-forming regions, not at the doorstep of a supermassive black hole. The paradox of youth forced a rethink of what is possible near a galactic nucleus. The orbits of many of these stars are confined to a common plane, almost like a miniature galaxy within the core, suggesting they indeed formed together from a disk of gas that somehow settled briefly amid the turmoil. The discovery of this stellar disk, essentially a ring of young stars, was a revelation that even in the black hole's shadow, star formation had found a way. Not all of the youthful stars sit neatly in the disk, however. Some race along wild, inclined orbits that carry them even closer to the black hole. The most famous of these is called S2. This star swings in a highly elongated path that takes it perilously near the invisible giant. At its closest approach, S2 comes within about 120 astronomical units of the black hole, just a few times farther than Pluto is from our Sun. A stone's throw in cosmic terms. There, S2 hurtles by at a few percent of the speed of light, whipping around the bend with a velocity of over 7,000 kilometers per second. In just 16 years, this star completes one entire orbit, tracing an oval that allowed astronomers to watch, in real time, the effects of extreme gravity on its motion. During its closest swing, S2's light was stretched and its clock slowed, exactly as predicted by Einstein's theory of relativity. S2's survival and repeated visits so close to Sagittarius tell us that at least some stars were somehow delivered practically into the maw of the black hole, yet remain intact. An astonishing testament to the dynamics of this region. One might wonder how these wayward young stars, found themselves so perilously close to the black hole's jaws. One possibility is that they were not born there at all. Perhaps a whole cluster of stars formed at a safer distance and later drifted inward, gradually being pulled apart by the black hole's tides, so that only its core members survived to settle near the center. Or maybe some of these stars began in binary pairs in the outskirts and met a different fate. In a dramatic scenario, a pair of stars might have wandered too near the black hole. Its gravity could snatch one star into a tight orbit while flinging the other outward as a runaway. Like dance partners torn apart, the star left behind suddenly finds itself bound to the black hole, circling the abyss alone. Over time, interactions like these could populate the inner sanctum with refugees from farther out, stars that were born in relative safety, but later thrown into the lion's den. The notion that entire star clusters could wander into the black hole's domain opens another chapter of the story. If a cluster of thousands of stars sank toward the core, the outer stars would likely peel away under the tidal forces, leaving only the densest inner members to reach the vicinity of the black hole. Such an event could seed the galactic center with a fresh crop of young stars all at once. It might explain why so many stars near Sagittarius A appear to be of similar age, as if they were born together and only later moved inward. One puzzle leads to another. Astronomers are following the trail of these wayward clusters to understand how the galactic center is continually replenished with new stars despite its hostile conditions. Farther out from the immediate gravitational grip of the black hole, entire star clusters roam the central region like wandering tribes. Among them are the arches and the quintuplet clusters, rich gatherings of young, massive stars situated only a few dozen light-years from the galactic center. These clusters sparkle with some of the brightest and heftiest stars in the Milky Way, miniature star cities in their own right. They formed within the galaxy's inner territory, where gas and dust pooled densely enough to ignite bursts of starbirth. Now, as time passes, they drift and circle in the tidal field of the galaxy's core, edging gradually closer to the nuclear hub. It's as if the galactic center's gravity has cast a net, slowly drawing these stellar communities inward. Out beyond the innermost swirl of stars, the galaxy's heart draws in larger groupings, like a magnet pulling iron filings. As a cluster like the arches moves through the central region, it feels a constant tug from the black hole and the surrounding mass of the bulge. The gravitational pull on the cluster's near side is stronger than on its far side, a difference that begins to stretch and deform the cluster. Imagine the cluster as a tight flock of stars venturing into a crowded city. As it weaves among the existing masses, some members are tugged away, left behind like stragglers on a long journey. Stars at the outskirts of the cluster slip free, stolen by the galactic center's gravity, or scattered along the cluster's trail. What starts as a compact, self-contained family of stars can slowly unravel. Over thousands of orbits, the cluster's shape distorts, stretching into a stream of stars that wraps around the center. One by one, or in small groups, stars peel off and become part of the general stellar halo of the center, leaving the cluster's heart to press onward. Astronomers suspect that some of the young stars now orbiting near the black hole arrived in just this way, delivered by a cluster that was torn apart during its descent. In this in-spiral scenario, the cluster's dense core could survive the journey to the inner few light-years before finally dissolving, seeding the environment around the black hole with its most tenacious members. It's like a cosmic delivery service, ferrying stars from safer birthplaces into the most dangerous neighborhood. This would neatly explain why so many hot, massive stars of similar age swarm near Sagittarius A. They were born together elsewhere and later migrated inward as their birth cluster disintegrated. The very presence of the arches and quintuplet clusters today, hovering at a few dozen light-years out, suggests that the process might be ongoing. Those clusters could be the next to drift closer and contribute their stars to the galactic center. The Arches cluster, for instance, already shows signs of this fate. Its stars are so tightly packed that their mutual gravity fights to hold them together. Yet the cluster orbits only a few dozen light-years from the black hole, well within its sphere of influence. Astronomers have measured the Arch's motion and found it likely following a path that will carry it nearer to the center over time. In a few tens of millions of years, a mere blink on galactic timescales, little may remain of the Arches except a long, thin stream of stars, each continuing around the galactic core without their once cohesive family. One can imagine the ghost of the cluster passing by the black hole, a faint trace of its former brilliance scattered by tides. The quintuplet cluster, slightly older than the Arches, holds its own marvels. Among its stars is the Pistil star, an extraordinary supergiant so luminous that it has blown a vast bubble of gas around itself, known as the Pistil nebula. This bubble glows like a delicate lantern in infrared images, a testament to the power of a single star's outflow. Clusters like the quintuplet and Arches are not mere collections of stars. They are dynamic entities that shape their surroundings even as they travel. As these clusters plough through the central molecular clouds, their intense radiation and winds carve out cavities and send shock fronts rippling into the gas. They may even trigger new stars to form in their wake, by compressing some regions while quenching star formation in others. They are both passengers and influencers in the galactic center ecosystem. When clusters like these break apart, they do more than sprinkle stars near the black hole. They also inject energy and heavy elements into the environment. Many stars in such clusters are so massive that they will explode as supernovae long before the cluster's journey is complete. Those titanic explosions send shockwaves through the interstellar medium and forge new, heavy elements, enriching the galactic center with the products of stellar alchemy. The remnants of these explosions, neutron stars and stellar black holes, then linger like ghosts, becoming new denizens of the central region long after the parent cluster has vanished. In this way, migrating clusters not only replenish the star count near the core, but also help shape its chemical makeup and dynamic behavior. They deliver fresh fuel for future star formation and new seeds for the black hole's entourage of small companions. Amid the infalling clusters and wandering stars, the galactic center is also threaded by flowing rivers of gas. Approaching the black hole from various directions are wisps of ionized material, drawn inward like luminous streams converging on a drain. They form a feature often called the mini-spiral, a set of twisting, glowing filaments of gas orbiting and falling towards Sagittarius A. To an observer, it would look like delicate tendrils of light swirling around the dark central point, a cosmic whirlpool illuminated by the fierce starlight and radiation at the core. These graceful streamers carry clues about how gas migrates through the nuclear metropolis, sometimes even feeding the black hole itself. With the stellar dramas unfolding, we turn to these gaseous threads to witness another layer of complexity in the Milky Way's heart. Close to the center, interwoven among the star cluster, lies this delicate structure of gas, known as the mini-spiral. It's as if someone traced glowing trails in the darkness, forming a loose spiral pattern around the black hole. These trails are actually streams of ionized gas, primarily hydrogen that's been energized until it shines with a soft reddish glow. 3 main branches twist around. Astronomers poetically call them the northern arm, the eastern arm, and the western arc. One prominent streamer, known as the northern arm, flows almost straight toward the central black hole before curving sharply, as if a river of hot plasma were pulled in and then whipped around a bend. Another feature called the western arc forms a partial loop, possibly outlining the inner edge of a larger orbiting gas disk. In infrared and radio images, these filaments stand out like neon threads against the cooler backdrop, illuminated by the intense ultraviolet light from the young stars nearby. In reality, the mini-spiral is not a single coherent spiral like a pinwheel galaxy, but a collection of streamers and clumps on intersecting orbits. Like rivers converging in a delta, these gas flows may come from different directions, each drawn inward by the black hole's gravity. Where they collide or cross paths, they create turbulence and shock waves that ripple through the gas. We see this as bright knots and twists along the filaments, markers where the gas is being compressed and heated even further. The entire arrangement is transient on cosmic timescales. The streams constantly shift. Some portions may eventually spiral all the way in and disappear into the black hole. Others might break apart and dissipate, and new streams could form as fresh gas finds its way inward. It's a dynamic, ever-changing tapestry of gaseous threads. Observing the mini-spiral over the years, astronomers have tracked the motion of its clumps, watching them swirl around the center like leaves caught in a whirlpool. Some gas blobs race around at hundreds of kilometers per second, tracing out segments of elliptical orbits under the black hole's pull. By mapping their velocities, scientists can actually see the imprint of the black hole's gravity on these streams, much as floating debris reveals the currents in a whirlpool. In this way, the mini-spiral serves as a natural laboratory, a way to study how gas orbits and infalls in the extreme environment just outside the black hole's immediate grasp. Surrounding the mini-spiral, just a bit farther out, lurks a broader torus of gas and dust known as the circumnuclear disk. This donut-shaped belt of cooler molecular material orbits a few light-years from the black hole. Over time, pieces of this disk can fragment or funnel inward through gaps, feeding the mini-spiral's streams. One can imagine clouds from the circumnuclear ring leaking toward the center along narrow channels, then getting ionized and lit up as they join the spiral dance. The mini-spiral is essentially a snapshot of ongoing inflow, a glimpse of how our galaxy trickles fuel into its central black hole one stream at a time. It also hints at the connectivity of the galactic center's structures. The outer molecular ring, the inner mini-spiral, and the black hole are all linked in a continuous flow of matter. From time to time, astronomers have even caught sight of a particularly daring gas cloud venturing perilously close to the black hole. Such a cloud is stretched like taffy by tidal forces and heated until it glows in X-rays, before vanishing from view as it succumbs to gravity. A few years ago, a cloud nicknamed G2 provided a real-life example. It swooped in close to Sagittarius A around 2014, and astronomers eagerly anticipated a brilliant fireworks show as it was torn apart. Instead, G2 mostly survived its passage, glowing only modestly in X-rays, a whimper rather than a bang. This outcome surprised many, showing that even at the brink of the black hole, nature can defy expectations. Nonetheless, events like these remind us that the mini-spiral streams are not just pretty ribbons. They are the very fuel that can ignite the black hole's feasting. When one of these clumps does spiral in and meet its end, Sagittarius, a star may respond with a brief flare of energy, a flicker of light announcing that a meal has been consumed. Beyond the immediate swirl of the mini-spiral and the circumnuclear disk, the galactic center opens up into an expansive realm of dense clouds and unusual activity. This broader region, stretching a few hundred light-years across, is laden with molecular gas and dust, the raw material for future stars. It's often called the Central Molecular Zone, CMZ, and it serves as the hidden reservoir fueling much of the drama in the nucleus. To fully explore the heart of the Milky Way, we must wander through this zone of cosmic clouds, where some of the galaxy's most massive and mysterious condensations reside, such as the legendary Sagittarius B2. No other part of the Milky Way is quite like the CMZ. The galaxy's barred inner structure acts like a gravitational funnel, channeling gas inward from the spiral arms. As interstellar clouds flow along the Milky Way's bar, they pile up in this central zone, unable to slip straight into the black hole, nor back out into the main disk. Over time, this process has built up the huge concentration of gas we see. If we could watch the CMZ in fast forward, we might see clouds streaming inward along curved paths, orbiting the center, and occasionally crashing into each other. Each collision and close pass rearranges the gas, sometimes sending some inward to feed the core, sometimes triggering a burst of stars, and sometimes just stirring the pot. It's a constantly evolving scene, an ecosystem of clouds responding to gravitational tides and injections of energy from stars and supernovae. The CMZ is a vast, turbulent expanse of gas and dust spanning the innermost few hundred parsecs, several hundred light-years, of the galaxy. It is as though an enormous ring or necklace of clouds wraps around the galactic nucleus, thick with star-making potential. Although it lies at the galaxy's core, the CMZ is hidden from our direct view by intervening dust. To ordinary telescopes, the central zone is cloaked in darkness. Visible starlight is extinguished by thick clouds in our line of sight. Only by using infrared and radio waves, which can pierce the dust, have astronomers mapped this crowded district. When seen in those wavelengths, the CMZ emerges as a glowing wreath of emission, full of intricate structures. It curls around the nucleus in arcs and spurs, revealing just how extraordinary and distinct this region is compared to the placid outer galaxy. Astonishingly, the CMZ holds the majority of the Milky Way's dense molecular gas, tens of millions of solar masses of it, compressed into a relatively small volume around the center. If one could view it from above, the CMZ might look like a lopsided ring of glowing nebulae and dark dust lanes encircling the core, with streamers connecting clouds like beads on a string. This is the staging ground for both spectacular star formation and perplexing cosmic mysteries, all unfolding beneath a veil of dust that shields it from visible light observers. Among the colossal clouds in the CMZ, one stands out as a titan, Sagittarius B2. Located roughly 130 light-years from the galactic center, SCAR-B2 is one of the most massive molecular clouds in the entire Milky Way. It contains several million times the mass of the Sun in gas, crammed into a region only a few dozen light-years across. Inside this cloud are myriad dense cores, pockets where gravity is striving to gather material into new stars. The environment is incredibly rich in molecules. SCAR-B2 is often described as a giant cosmic chemistry laboratory. Within its depths, astronomers have detected a cornucopia of organic compounds, from simple alcohols to complex molecules that hint at precursors of life. The air, if one could call it that, inside SCAR-B, too, carries the spectral fingerprints of substances like formaldehyde and methanol, not to mention ethyl formate, a molecule that on Earth gives raspberries their flavor and rum its scent. One might say, in jest, that the center of our galaxy carries a whiff of fruity rum, though of course this cocktail of gases is far too thin and toxic for any human to smell directly. Even amino acid-like molecules have been reported in SGB2's mix, hinting that some basic ingredients of life are adrift in space there. Deep within, new stars are trying to ignite. Astronomers find telltale signs in the form of masers, intense beams of microwave emission produced by excited molecules like water or methanol in dense clumps. These masers act like cosmic beacons, pinpointing the locations of embryonic stars or strong shocks in the cloud. In a sense, they are the neon signs of the galactic center, advertising where extreme conditions prevail. By tracking maser spots, scientists can measure motions and even distances with exquisite precision, observing how parts of SGRB2 orbit or collapse. Visible light cannot escape SGRB2's opaque shroud, but in radio and infrared, this cloud lights up with evidence of ongoing star formation in its veiled interior. Dozens of newborn stars are probably forming inside, each heating and stirring its own small neighborhood of gas. But SGRB2 is just one character in the CMZ's story. There are other immense clouds, each with its own tale. One such cloud, often nicknamed the Brick for its blocky appearance in radio maps, is staggeringly dense, yet surprisingly inert. Despite containing enough mass to form tens of thousands of stars, the Brick shows almost no signs of star formation. It sits in eerie silence, as if waiting indefinitely for a spark to set it ablaze. The Brick has become a symbol of the galactic center's star formation puzzle, a powder keg of material that stubbornly refuses to ignite. Astronomers watch it with fascination, wondering what event might finally trigger it to light up with new stars, or if it will remain a quiet enigma for ages to come. Meanwhile, not far away, another cloud might be teeming with newborn stars and glowing with HYY regions as young stars ionize the gas around them. This patchiness, some clouds bursting with activity, others strangely quiescent, puzzles researchers. Why do some clouds in the CMZ readily birth stars, while others, equally massive, remain dormant? The answer seems tied to subtle differences in conditions and timing within this extreme environment. Part of the answer lies in the CMZ's extreme conditions. The gas here doesn't sit still. It churns and flows at high speeds. Measurements show that clouds in the CMZ have internal motions of tens of kilometers per second, turbulence on a colossal scale. When two gas streams collide, they send shock waves through the region. Shocks can heat and compress gas, and they also knock molecules off dust grains, enriching the molecular stew. In fact, certain molecules found in abundance, such as silicon monoxide, SiO, are telltale signs that strong shocks are shattering dust particles and releasing silicon into the gas. The CMZ is as much a battleground as it is a nursery. Cloud crashes, magnetic eruptions, and supernova explosions keep it stirred up, making it a dynamic and often violent environment. Evidence of these energetic interactions can be seen in structures like Sagittarius A East, a bubble-like supernova remnant near the center. SGR A East appears to be the aftermath of a massive star's explosion, perhaps tens of thousands of years ago. Its expanding shock front is ploughing into nearby molecular clouds, including one known as the 50 km per second cloud, named for its distinct velocity. As the shock slams into dense gas, it excites molecules and triggers brilliant maser flares, essentially lighting up the clouds at the collision sites. We see arcs and shells in radio and X-ray maps, where the supernova's blast wave is ramming into the CMZ's material. SGR A East's influence is a vivid reminder that the central molecular zone is continually shaped by both the creation of stars and their explosive demise. Every so often, a supernova goes off like a pressure release valve, stirring the surrounding clouds and injecting new energy into the mix. Beyond the striking sights of clouds and clusters, there is an invisible framework threaded through the CMZ. It reveals itself subtly, through the polarization of starlight, the alignment of dust grains, and most dramatically through radio-emitting filaments. Yet it is highly influential. These are the magnetic fields that permeate the region, powerful and surprisingly organized. In fact, evidence of their presence is striking. The galactic center is laced with unusual radio filaments, long and thin threads that glow with high-energy particles spiraling along magnetic lines. As we venture further, these magnetic threads come into focus, adding another piece to the Milky Way's hidden heart puzzle. Throughout the galactic center, strange, slender threads of energy streak through space, visible only to radio telescopes. These are the non-thermal filaments, mysterious strands that extend for tens of light years, yet are only a fraction of a light year across. They often hang perpendicular to the Milky Way's disk, like glowing wires in the dark, emitting radio waves rather than visible light. The sight of these filaments startled astronomers when they were first observed, since nothing like them had been seen elsewhere in the galaxy's quieter suburbs. One of the earliest found was the so-called radio arc near the core, an almost perfectly straight filament that rises high above the galactic plane. Another, nicknamed the snake, meanders in a sinuous curve, as if tracing invisible currents in the galactic heart. These structures defied explanation at first. They don't line up with spiral arms or any usual pattern of gas, but instead hint at an underlying magnetic grid. Over time, more filaments were uncovered, each adding a piece to the puzzle of this hidden magnetic architecture. First discovered in the 1980s, the filaments have since been revealed in the hundreds by modern telescopes like Meerkat, proving that magnetism is a dominant force woven through the heart of our galaxy. Each filament is essentially a beam of high-energy electrons spiraling around magnetic field lines at nearly the speed of light. As these electrons gyrate, they produce synchrotron radiation, the same phenomenon that makes particle accelerators on Earth glow with eerie light. The brightness and coherence of the filaments suggest astonishingly strong and orderly magnetic fields threading the region. In places, the field strength might be dozens of times greater than the typical magnetic field in the Milky Way's disk. The filaments act like cosmic neon tubes, lighting up to show us where these intense magnetic highways run through space. They cluster predominantly around the center, forming a kind of magnetic scaffolding that towers above and below the plane. Recent observations with powerful radio telescopes like South Africa's Meerkat have revealed that these filaments are not rare at all. There are hundreds of them threading the central region. They appear in bundles or groups, sometimes evenly spaced like harp strings. Intriguingly, they are found only near the galactic center, a signature feature of this environment, not observed out in the calmer disk of the galaxy. This underscores just how special the conditions are in the nucleus. Some filaments seem to emanate from around the central black hole itself, or from past energetic events, hinting they could be remnants of ancient outbursts or channels guiding current flows of particles. In fact, astronomers recently found a second family of filaments, shorter horizontal threads that spread out radially from the center like fragmented spokes on a wheel. Each of these horizontal filaments is 5 to 10 light-years long and appears to point back toward the black hole. They may be remnants of a blast of material from Sagittarius A about 6 million years ago, an outflow that slammed into surrounding gas and stars, creating streaks of hot plasma aligned with that eruption. The effect is akin to blowing blobs of paint outward with a hairdryer. The outflow from the black hole distorted and stretched anything in its path, leaving behind filaments pointing away from the center. The discovery of these radial strands alongside the long vertical filaments provides even more clues about past activity in the core, hinting at blasts of wind or jet-like emissions that have shaped the magnetic landscape. Taken together, the vertical and horizontal filamentary structures paint an ever richer picture of the galactic nucleus, revealing how magnetism and outflows have sculpted this region over time. In addition to individual threads, astronomers have discovered gigantic radio bubbles billowing out from the galactic center, each extending hundreds of light years above and below the plane. These balloon-like lobes are also laced with filaments, as though the magnetic field lines were blown outward and illuminated by the same energetic particles. The presence of such bubbles suggests that at some point in the recent past, perhaps a few million years ago, an enormous eruption of energy occurred in the nucleus. It could have been a burst of star formation, resulting in multiple supernovae, or a period of intensified feeding by the black hole, maybe both. Whatever the cause, the result was twin lobes of hot plasma expanding north and south of the disk. The filaments outline these bubbles like glowing striations, giving us a spectacular visual hint of how powerfully the center can affect its surroundings when it blows its top. It's as if the galactic center took a deep breath and exhaled in two giant puffs, and the magnetic filaments were carried along for the ride. All these magnetic structures do more than glow. They channel and control the flow of cosmic rays through the central zone. Like unseen travelers, high-energy particles race along the magnetic threads and diffuse throughout the region, colliding occasionally with gas and dust. In doing so, they ionize atoms and gently heat the material, quietly but persistently. The elevated temperatures of the molecular clouds and the curious chemical ionization we observe can be traced in part to this hidden interplay between cosmic rays and magnetic fields. As we follow these clues, we turn to examine how cosmic rays, those invisible energetic visitors, and other factors raise the heat in the galactic center, and why this environment runs hotter than expected. The galactic center is suffused with an invisible rain of high-energy particles. These cosmic rays, born in supernova shockwaves and perhaps in past black hole eruptions, race through space at nearly light speed, permeating the interstellar gas like an intangible cosmic wind. If one could stand at the galactic center, miraculously shielded from other dangers, they would be bathed in radiation far beyond Earth's background levels, a silent drizzle of high-energy particles passing through every fiber of their being. One telltale effect of this cosmic ray bath is the widespread ionization of hydrogen molecules. In the CMZ, astronomers measure ionization rates hundreds of times higher than in the quiet outskirts of the galaxy. That means the gas is constantly being zapped by energetic particles, transforming some neutral hydrogen into charged H2+ and H+, leaving behind a distinct chemical fingerprint that we can detect. For any inhabitants of this region, purely hypothetical given the harsh conditions, the effects of cosmic rays would be pervasive yet largely unseen. But one key consequence of all this invisible bombardment is heat. Cosmic rays quietly warm the gas from the inside out. Unlike the cold molecular clouds elsewhere in the galaxy, which often linger at only tens of degrees above absolute zero, the clouds in the central zone are remarkably warm. Many dense clouds near the nucleus have temperatures of 50 to 100 Kelvin, degrees above absolute zero, and some diffuse gas phases reach even a few hundred K. This warmth is puzzling because, although the region is full of stars, there isn't enough starlight alone to heat all that gas so uniformly. Instead, the heat seems to come from within, from cosmic ray bombardment and turbulent stirring on a microscopic scale. To probe this phenomenon, scientists use molecular tracers as thermometers and signposts. For example, the molecule ammonia, NH3, emits radio waves that reveal gas temperature. In the galactic center, ammonia indicates that dense gas is significantly hotter than in typical giant clouds. Another tracer, the ion H3+, is found in surprisingly high abundance. It's a fragile molecule that exists only where ionization is intense. effectively serving as a cosmic ray counter. These measurements all point to the same conclusion. Something is persistently pumping energy into the clouds, keeping them warmer and more ionized than expected. Cosmic rays are a prime suspect. Every time a massive star goes supernova in the central region, it accelerates swarms of particles to near light speed, which then wander through the surrounding space for millennia. With numerous massive stars and frequent supernovae over the eons, the cosmic ray density has built up. Additionally, the supermassive black hole itself can accelerate particles during its occasional flares, adding to the high-energy population. The strong magnetic fields near the center corral many of these particles, making the CMZ a reservoir of cosmic rays that continue to stir up the gas long after their initial launch. Interestingly, these energetic particles heat the gas more efficiently than they heat dust. In most of the galaxy, dust grains absorb starlight and warm the surrounding gas. Gas and dust temperatures go hand in hand. But in the CMZ, observations show gas temperatures exceeding those of the dust. This inversion implies a non-standard heating source is at work. Cosmic rays fit the bill. They penetrate deep into clouds, ionizing and exciting atoms and molecules directly, whereas dust grains might stay cooler without enough light. The result is an environment where, even in the absence of strong local heating sources like young stars, the gas remains in a tepid, simmering state rather than cooling down to quiescence. All this extra energy in the gas doesn't just make things warmer, it also changes the rules for star formation. Warm, ionized gas resists gravitational collapse. Its pressure fights against compression. Likewise, turbulence and magnetic fields stiffen the clouds, providing support that counteracts gravity's pull. Thus, in the galactic center, the threshold for forming new stars is higher. Despite an abundance of raw material, the region forms stars at a slower pace than one might expect. As one researcher quipped, it's as if the galactic center's clouds are on strike, refusing to collapse until conditions are absolutely perfect. This conundrum leads us to the next piece of the puzzle: star formation under stress. How stars are born, or not, in such a tumultuous environment. Despite the enormous amount of gas in the CMZ, the birth of new stars is curiously subdued. By many measures, the galactic center should be a bustling stellar nursery, yet it isn't. Astronomers have noticed that the star formation rate in this region is roughly an order of magnitude lower than one would expect, given the vast fuel available. In other parts of the galaxy, and in galaxies beyond, more gas almost always means more stars. It's a kind of galactic rule of thumb. But here at the center, that rule seems to bend or break. In effect, a kind of cosmic suppression is at work. Raw material is everywhere, but the clouds appear unwilling or unable to collapse and form stars at their usual efficiency. The culprit behind this inefficiency is the extreme environment itself. The recipe for star formation normally calls for cold, dense gas that can quietly condense under gravity's pull. But in the galactic center, the gas is rarely quiet or cold. High temperatures, intense turbulence, and strong magnetic fields all conspire to prop up the clouds from within. They generate pressure and support that counteracts gravity. A cloud that would readily collapse into stars in a calmer galactic suburb might hold itself up here, like an overstirred souffle that refuses to set. The gas is stirred and heated to the point that gravity has to work much harder to overcome the internal motions and start forming stars. In practical terms, star formation in the CMZ is quenched, not totally halted, but significantly slowed and less efficient than expected. Moreover, the very gravitational forces that draw material inward can also hinder local collapse. Closer to the black hole, tidal forces stretch and shear clouds, unless they are exceedingly dense. This sets a formidable threshold. Only the most compact and massive clumps can overcome the disruptive tides and begin forming stars. Many potential stars are nipped in the bud, their nascent clumps torn apart or dispersed before a new star can fully develop. In essence, the central region raises the bar for star birth. It permits only the most robust seeds to grow. This idea is backed by observations of the region's dense cores. They often have to reach extraordinary densities, many times higher than typical star-forming cores elsewhere, before gravity wins out. It's survival of the fittest, in the most literal sense for star formation. Yet, under the right circumstances, star formation does ignite in the galactic center, often dramatically. It seems to take an extra push or collision to tip the scales. One cloud might drift for ages in a metastable state until a supernova's shockwave slams through it, providing the trigger. Or as gas streams orbiting the center converge and pile up, for example, where the elongated orbits crowd together along the innermost ring of the CMZ, they can spark bursts of star formation. Astronomers suspect the central zone experiences episodic bursts of star birth, followed by lulls, rather than a steady drizzle. A major event might light up several massive clusters at once, as perhaps happened a few million years ago, giving us the arches and quintuplet clusters, and then the region may fall relatively quiet again for an extended period. The process is stop and go, like a heartbeat or a series of fireworks, rather than a constant glow. Clouds like the Brick might be ticking time bombs that simply haven't detonated yet, waiting for that extra push, while others have gone off in the recent past and left behind clusters as evidence. Interestingly, when stars do manage to form in these extreme conditions, they tend to be on the heavy side. The clusters born in the CMZ often contain an unusually high fraction of massive stars, suggesting the initial mass distribution of new stars, the IMF in astronomers' terms, may be skewed. It's as though the same conditions that suppress star formation also favour the few stars that do form to be giants. The arches and quintuplet, for example, are overflowing with stars much larger than our Sun. This top-heavy outcome could be because only the most massive clumps can collapse here, and those clumps naturally produce massive stars. So the galactic center's star-making, when it finally happens, produces spectacular beacons that live fast and die young, ending as supernovae or even black holes. In this way, the difficulties of star formation under stress lead to an interesting payoff. Fewer stars form, but those that do are often cosmic heavyweights, capable of seeding the next generation with lots of energy and enriching elements when they explode. The aftermath of these stellar lives adds yet another ingredient to the galactic center's ecosystem. When a massive star dies here, it leaves behind a compact corpse, a neutron star, or a black hole. Over countless generations, such remnants are predicted to congregate near the middle, drawn in by the pull of the supermassive black hole and a process known as dynamical friction, where heavier objects gradually sink toward the center by stirring up lighter ones. The galactic center should be teeming with these unseen companions, a hidden population of stellar black holes and neutron stars orbiting among the crowd. Uncovering these stealthy residents is a challenge, but their presence is crucial to completing our picture of the nuclear metropolis. Our journey now shines a light on these black hole companions and the subtle role they play alongside the central monster. The supermassive black hole is not as solitary as it might appear. Surrounding it, hidden in the dense star cluster, are thought to be countless smaller dark objects, stellar mass black holes and neutron stars, the remnants of bygone stellar generations. Over the Milky Way's lifetime, many massive stars have lived and died near the core, each death leaving behind a compact remnant. Over time, these heavy remnants tend to migrate inward, gradually congregating in the black hole's neighborhood like iron filings drawn to a magnet. In effect, Sagittarius A sits at the center of a swarm of smaller companions, an invisible entourage of dark stars paying court to the galactic king. If we could somehow illuminate this hidden population, we might see hundreds or thousands of faint companions orbiting the central black hole. They form a kind of dark halo around Sagittarius A, like a swarm of ghosts bound to an even greater phantom. Most of the time, these remnants are practically invisible. Black holes emit no light on their own, and inactive neutron stars glow only feebly, like cold embers. Yet occasionally, one betrays its presence. A stellar black hole might capture gas from a passing star, or rip material from an unlucky neighbor, flaring to life as an X-ray binary. In those moments, it shines brightly as it devours matter, giving off high-energy X-rays that observatories can detect. Astronomers have observed mysterious X-ray flashes and gamma-ray bursts in the central region that likely signal such events. Smaller black holes briefly igniting when they feed. These flashes are like the momentary growls of a pack of hidden predators in the jungle. You seldom see them, but you catch glimpses of their ferocity. One particularly intriguing discovery occurred in 2013, when a rare kind of neutron star, a magnetar, was detected surprisingly close to Sagittarius A. Magnetars are neutron stars with incredibly strong magnetic fields, and this one's radio pulses managed to pierce the dense intervening plasma enough to be detected on Earth. Its presence so near the black hole was both unexpected and fortuitous. Not only did it provide a new probe of the conditions around the black hole, for instance, its radio signals helped measure how much interstellar electrons and magnetic effects exist near A star, but it also confirmed that neutron stars can indeed survive in this tumultuous environment. This magnetar gave astronomers hope that many more pulsars, rapidly spinning neutron stars emitting beams of radio waves, might lurk near the galactic center, their signals hidden by distance and scattering. Despite the magnetar's discovery, a long-standing mystery remains. Where are all the other pulsars we expect to find at the galactic center? Models predict that hundreds of neutron stars should be orbiting within a few light-years of SGRA, remnants of past star generations. Yet searches in traditional radio bands have found very few. The likely culprit is the medium between us and the center, ionized gas and interstellar fog that can scatter and dim pulsar signals. It's as if a thick haze lies between us and these cosmic lighthouses, smearing their pulses into an unrecognizable blur by the time they reach Earth. New techniques and higher frequency observations are being pursued to penetrate this haze. The magnetar's radio pulses, for instance, had to be observed at high frequencies where scattering is less severe to be detected. As technology improves, astronomers hold hope that one day they will tune into the chorus of pulsars hidden at the Milky Way's heart, using them as precise tools to measure the black hole's properties and the gravitational environment with unrivaled clarity. This unseen menagerie of black holes and neutron stars means the central black hole is attended by a court of stellar remnants that help shape the dynamics of the core. Once in a great while, one of these black holes might spiral directly into the giant, merging with it and sending faint ripples through spacetime, gravitational waves echoing across the galaxy. Such an event would slightly pudge up the big black hole and create a telltale burst of gravitational waves, perhaps detectable with future observatories. In other cases, their collective gravity and energy stir the surrounding gas and stars, contributing to the perpetual hustle of the nucleus. Far from being a solitary king, Sagittarius A rules alongside these dark companions, each subtly influencing the environment. Understanding this swarm is essential to grasp how the galactic center regulates itself and evolves. It's the interplay of all these constituents, stars, gas, magnetic fields, and black holes big and small, that creates the delicate, self-balancing cosmic neighborhood at the galaxy's core. In the chaos of the galactic center, a kind of order emerges, a balance forged by cycles of energy and calm. When gas accumulates and conditions ripen for new stars to form, or for the black hole to feed more actively, that very activity soon triggers its own suppression. Massive stars may burst into being and blaze for a brief epoch, but their fierce winds and eventual supernova deaths inject turbulence and heat back into the surrounding clouds, preventing too many more stars from forming immediately. Similarly, if the black hole were to gulp down a large meal of gas and briefly flare up, the outburst would blast radiation and maybe even jets outward, stirring and heating the remaining gas. These feedback processes act like a thermostat, ensuring that neither star formation nor black hole growth runs away unchecked. The galactic center seems to teeter around an equilibrium, where a surge in activity leads to a quelling response, keeping the system in balance over the long run. We see evidence of this self-regulation imprinted all over the central region. The relatively modest current activity of Sagittarius A, it flickers now and then, but is generally quiet, suggests it's in a quiescent phase, perhaps because previous outbursts blew out or heated the gas that would otherwise be fueling a bright flare today. Likewise, the abundance of warm, turbulent gas and the lack of a massive ongoing starburst hint that the last big burst of star formation, maybe a few million years ago, injected enough energy to keep things stirred up since then, suppressing another burst for now. Even the giant radio and gamma-ray bubbles towering above the galactic center, faint echoes of an energetic past, likely mark a period when the black hole, or a flurry of supernovae, or both, pumped huge amounts of energy into its surroundings. That event, perhaps around 6 million years ago, effectively vented the system. It blew hot plasma out of the disk and into the halo, carrying away excess energy and angular momentum. In the aftermath, the center would have entered a quieter state, slowly accumulating fresh gas again until the next cycle. The bubbles we detect today gradually fade, while the core gears up for the next act in its ongoing drama. Over millions of years, the center of our galaxy likely goes through beats of activity, almost like a heartbeat or the inhaling and exhaling of a lung. A burst of star formation here, a spurt of black hole feeding there, then a period of calm. During the calm, gas clouds can resettle, cool down somewhat, and collect in the central zone. Eventually, enough gas accumulates, or some external trigger arrives, and a new pulse of activity ignites. Another cluster of stars, another mini outburst from the black hole. In this cyclical way, the nucleus maintains an overall equilibrium. It never completely empties its fuel in one go, which would result in a huge one-time blaze and then long starvation. But it also never allows gas to pile up indefinitely without any consequences. Each generation of stars and each flicker of the black hole carries the memory of the last event and helps set the stage for the next, in a continuous feedback loop that has likely been operating for billions of years. This self-regulating behavior might be the key to the Milky Way's longevity. By preventing runaway starbursts or an unchecked quasar-like blaze at the core, the galaxy avoids destroying its structure or exhausting its fuel too quickly. The energy returned by one active phase sustains the lull of the next. It's a delicate balance. Too much activity, and the reserves get blown out into intergalactic space. Too little activity, and the core might collapse too efficiently or become unstable. But nature has found a middle path. The galactic center, for all its eruptions and lulls, remains remarkably steady when viewed on cosmic scales. Other galaxies likely follow similar patterns. Some galactic cores blaze furiously as quasars until feedback quenches them. Others flicker along quietly, having already reached equilibrium. Our Milky Way sits somewhere in between, active enough to be interesting, calm enough to endure. In our galaxy's heart, we glimpse a general principle of the cosmos: creation and destruction in a constant dance, finding a harmonious rhythm that can last eons. Even as we begin to decipher this intricate cosmic neighborhood, many mysteries remain. How exactly does the black hole's occasional fury sculpt the fate of future stars? What roles do unseen forces and subtle interactions play in the grand scheme of this ecosystem? The hidden heart of the Milky Way invites us to continue our exploration, promising that with every deeper look, new wonders will emerge. For now, we leave this nuclear metropolis in a state of dynamic equilibrium, a testament to the galaxy's ability to regulate its own heartbeat amid turmoil. And as our journey through this realm of darkness and light goes on, we carry a deepened appreciation for the complex, self-sustaining symphony playing out at the center of our home galaxy. Picture the scene at the very center of our galaxy, some 26,000 light-years away. There, a dense swarm of fast-moving stars circles an invisible dark presence. It is a bustling region, bathed in the glow of countless suns and threaded with hot gas. At the core of this cosmic city lies a void, a supermassive black hole, silent and hidden from direct view. Were you able to float in that central realm, you would witness a sky ablaze with stars whipping around at incredible speeds. The black hole itself would reveal its presence only through their dance, an unseen master at the center of a brilliant orchestra. This is the Milky Way's heart, a place of extreme gravity and deep mystery, a central engine quietly influencing the cosmic metropolis around it. The colossal black hole at the galaxy's core remains a surprisingly quiescent presence, a sleeping giant in the bustling cosmic city. Stars crowd around this dark heart, yet the giant seems to slumber, emitting only faint whispers of energy. It is a quiet behemoth, sustained by only the thinnest trickle of cosmic nourishment. In this gentle hush, one might wonder, how does such a gravitational titan sustain itself at all, surrounded by light and life, yet rarely stirring? For now, it rests in near silence, stirring only faintly as the ages pass by. Despite its hunger, the black hole is surrounded by plenty of potential food, diffuse streams of gas and dust, and the stellar winds that blow fiercely from young stars nearby. These massive stars act like cosmic gardeners, shedding gas in all directions, and some of that tenuous material drifts toward the waiting giant. Yet feeding a black hole is not so simple. Most of the gas carries a whirl of motion, an angular momentum that keeps it swirling around the black hole rather than plunging straight in. Like water circling a drain, the material orbits, trapped by its own sideways momentum, forming a sparse, hot halo around the dark center. To truly picture this, imagine water swirling around a drain. If the water spins fast enough, it circles the drain for a long time without going in. Similarly, the gas near the black hole orbits in loops, held back by its own momentum. Without a way to slow down and lose that sideways motion, it cannot drop directly into the hole. Only when friction or collisions between gas streams sap away some of that energy can the material spiral inward. It's a delicate dance of gravity and motion. And for the most part, motion wins, keeping the feast tantalizingly out of reach. For all the black hole's mighty gravity, Its innermost grip is surprisingly small, a narrow region near the event horizon where matter can truly plunge inward. Most of the gas stays safely beyond that fatal boundary, spinning in a kind of holding pattern rather than falling straight down. Indeed, despite the fierce stellar winds all around, only a tiny fraction of their cast-off gas ever loses enough momentum to spiral into the abyss. The rest races around or escapes back into the galactic haze, leaving the black hole with only a meager taste of the feast that surrounds it. The quiet giant lives on lean pickings, sustained by scraps of the abundant matter swirling nearby. It is as if an enormous creature sits at a banquet, but can only sip broth rather than devour the meal before it. From time to time, larger clumps of matter wander into the black hole's vicinity. Perhaps a drifting cloud nudged inward from farther out, or a dense knot of gas dislodged by some gravitational interaction. If a clump strays close enough, the giant's gravity seizes it, pulling it into orbit like a moon drawn to a planet. But capture alone does not guarantee a full meal. Even as the clump circles the darkness, it must unravel and collide with other material to shed its energy. Gradually, friction and turbulence sap the clump's orbital dance, slowing it down. Bit by bit, the once distant cloud can then spiral closer, inching toward the point of no return and feeding the quiet giant in a drawn-out, delicate process. Most days and years pass, with the black hole merely picking at crumbs, never truly breaking its fast. But the cosmos is full of surprises, and once in a while, a larger morsel finds its way down into the darkness. When this happens, the quiet giant awakens a bit from its drowsy state. A flare of energy erupts as the black hole hastily devours the unexpected bounty. These rare feeding episodes are fleeting, yet they illuminate the otherwise dim heart of the Milky Way with a sudden, if temporary, brilliance. In those moments, we catch a glimpse of what a hungry giant can do when offered a hearty meal. Astronomers have learned that the black hole's meals often come in spurts, rather than as a steady flow. One dramatic example arrived in the early 2000s, when a mysterious cloud of gas, known as G2, was observed on a path toward the galactic center. For years, telescopes tracked this ethereal clump as it drifted closer, drawn in by the gravity of the dark heart. Many anticipated a cosmic show. As G2 swung near, the black hole might tear it apart and light up in a brilliant flare of accretion. In mid-2013, G2 reached its closest approach, and the tidal forces from the black hole stretched the cloud thin, like taffy being pulled apart. Then G2 vanished from telescopic view as it swung behind the black hole's domain. Yet the expected fireworks were subtle at best. Instead of a furious feeding frenzy, Sagittarius, a star, barely stirred. The black hole's output rose only modestly, a far cry from the anticipated blaze. It turned out G2 might not have been a mere cloud after all, but perhaps a star cloaked in gas and dust, a resilient core that survived the black hole's tidal grasp. If so, the encounter was more like a grazing bite than a full meal. The object continued on its orbit, battered but intact, leaving only a trace of its outer layers behind to be captured. SGR-A star may have snacked on those scraps, producing a minor uptick in energy, but nothing like the grand eruption scientists had hoped to witness. G2 was not the only enigmatic traveller. Another object, dubbed G1, had slipped past the black hole about a decade earlier, also without triggering any major outburst. Since then, astronomers have identified several more of these peculiar G objects orbiting near the galactic center. Each looks diffuse and cloud-like from afar, but their repeated survival in the black hole's vicinity hints at something sturdier hidden inside. Perhaps a star, enveloped in an extended shroud of gas. One idea is that these are stars that have merged or become strangely bloated, swaddled in gas and dust from their own outer layers. When such an inflated star swings close to the giant, tidal forces tug at its envelope, peeling off gas and dust like wisps of cotton. Those stripped fragments then drift toward the black hole and are consumed, delivering a brief and modest surge of energy. Each encounter is a gentle feeding, an episodic delivery of fresh material that momentarily rouses the quiet beast from its slumber. Occasionally, the sleeping black hole flares into activity, seemingly out of nowhere. One remarkable instance occurred in May 2019. On a calm night that month, Sagittarius, a star, suddenly brightened to an unprecedented degree in infrared light. For a brief moment, it glowed tens of times more intensely than normal. A beacon in the darkness, where before there had been only a faint shimmer. The sudden burst was unexpected and tantalizing. Perhaps the black hole had gulped down a particularly dense clump of matter, or an unstable region in its disk suddenly dumped material into the abyss. Within hours, the flare subsided, and the giant fell back into quietude, leaving astronomers abuzz with excitement and new questions. This rare outburst was a vivid reminder that the quiet giant's appetite can ignite without warning, offering a momentary glimpse of its latent power. Some researchers speculated that it might have been delayed fallout from G2's encounter years earlier, gas from that cloud finally making its way into the black hole. Others proposed it was an unrelated event, illustrating just how unpredictable the black hole's episodic appetites can be. Feeding a black hole is not a one-way street. Each time the giant consumes matter, it also releases energy back into its surroundings. In fact, even as it quietly hungers, Sagittarius, a star, is constantly breathing subtle streams of particles and radiation outward, a cosmic sigh that follows each tiny gulp. This exchange means that whenever the black hole dines, it also stirs the space around it. Energy and matter that do not disappear past the horizon are flung back into the galaxy in winds and outflows, spreading the effects of each feeding far and wide. Even in its quiescence, the black hole is not entirely still. It exerts a steady influence on its surroundings, gas that drifts inward towards Sagittarius. A star doesn't all vanish. Much of it gets heated and flung back out into space. The result is a persistent outflow, a breeze of hot plasma wafting away from the galactic center. It is as if the giant exhales, even as it inhales, maintaining a delicate balance. This wind is not a raging storm, but a gentle, steady breath in cosmic terms. A sub-relativistic breeze carrying particles outward at thousands of kilometers per second. In a way, the black hole's behavior is reminiscent of a slumbering volcano, mostly calm, but always releasing a hint of hidden power. Even in apparent dormancy, one can imagine a slow, steady breath, a faint stream of particles and energy drifting outward. This gentle outflow is like the creature's soft exhalation, a subtle reminder that beneath the stillness lies tremendous energy. It is a quiet sign of life from the darkness, maintaining the black hole's presence in the surrounding space, despite its current silence. Astronomers have found hints of this outward breeze through careful observation. X-ray and radio images of the galactic center reveal faint wisps of energized gas stretching away from the black hole, as if tracing the paths of particles being flung outward. These subtle structures suggest that material is indeed flowing out from the core. For an ostensibly quiet nucleus, even such delicate motions speak volumes about the unseen power at work. Though far from the focused, near light-speed jets of active galaxies, this wind still moves fast. Its particles zip along at a few percent of light speed, gentle by cosmic yardsticks, but astounding by human standards. Such a flow carries substantial energy and momentum, enough to buffet and heat the surrounding gas as it expands. In the black hole's energy budget, much of the power from infalling matter never emerges as light for us to see, but instead goes into propelling this mass of gas outward. By the time a bit of matter either slips past the horizon or is flung back out, its gravitational energy has been split. A small portion illuminates the surroundings, while a larger share rides out on the outflow, dispersing into the wider environment. Astronomers detect hints of this outward breeze in multiple ways. Telescopes, sensitive to X-rays and radio waves, see filaments and wispy structures pointing away from the center, as if sketching the outline of escaping particles. The outflowing gas is swift, perhaps thousands of kilometers each second, only a tiny fraction of light speed, yet substantial enough to shove aside other material in its path. These winds carry away a sizable portion of the energy liberated by infalling matter. In fact, the black hole's feeble glow hides the true scale of power at play. For every bit of mass that drips into the abyss, much of its energy is channeled not into visible light, but into the motion of heated gas blowing outward. By the time the transaction is done, the giant has taken its cut, but an equal or greater share of energy has been deposited back into the environment around it. The presence of these winds and outflows is a sign that even quiet black holes leave their mark on their surroundings. Though today's breeze is relatively gentle, the galaxy carries memories of times when the giant's exhalations were far more intense. Just as a shout in a cavern can send echoes rippling through the air long after the shout itself has ended, a burst of energy from the galactic center can reverberate through space. In the case of our black hole, those reverberations can actually be seen, reflecting off distant clouds and preserving a record of past outbursts. Through these delayed signals, we are able to glimpse flashes of the Milky Way's hidden heart as it was long ago, during one of its more boisterous episodes. The Milky Way's central black hole may be quiet now, but the surrounding cosmic neighborhood holds echoes of a more energetic past. Some of the giant clouds of gas in the galactic center region are mysteriously glowing with X-rays, as if they briefly became X-ray sources themselves. Yet these cold molecular clouds have no internal power to produce such high-energy radiation on their own. Instead, they behave like cosmic mirrors, illuminated by a flash that came from elsewhere. It is here that the black hole's hidden history reveals itself, preserved in faint, delayed reflections of light. Imagine, for a moment, a powerful burst of X-rays erupting from the galactic center some centuries ago. At the time of the eruption, Earth's sky would not have revealed anything unusual to our distant ancestors. Such a high-energy flash was invisible without modern instruments. Yet the burst occurred, and its X-ray light raced outward from the galactic center at light speed, spreading through the surrounding void. This was the beginning of an echo, a signal that would wander through space only to be heard long after the original shout had faded. Years after the initial flare, that wave of X-rays finally reached a far-off target, a massive cloud of gas and dust floating dozens of light-years away from the black hole. When the surge of radiation struck this cloud, it did not simply pass through. The cloud's atoms absorbed the energetic rays and promptly re-emitted them, causing the entire cloud to light up briefly in X-rays. For a short time, the cloud itself became a beacon, shining with the borrowed energy of the long-vanished flare. This scenario is not just a thought experiment. Actual observations back it up. In the early 2000s, astronomers using space telescopes noticed that a gigantic molecular cloud, unassumingly named Sagittarius B2, was glowing with unexpected X-ray brightness. For such a cold, dark cloud to shine in X-rays at all was a startling clue. Intriguingly, over the following years that cloud's X-ray glow began to fade, as if a cosmic spotlight were slowly dimming. The leading explanation is that Sagittarius A star produced a huge flare about a century ago, and Sagittarius B2 is acting as a distant mirror for that event. By studying the cloud's fading light, scientists deduced that during that long-ago outburst, the black hole blazed perhaps millions of times brighter than it does today. It was a brief resurgence of activity for our galaxy's heart, a kind of cosmic flicker that nobody on Earth could witness at the time. In this way, the cloud served as a time capsule, preserving the memory of the black hole's awakening and delivering it to us, decades or centuries later, as a faint echo in the darkness. Sagittarius B2's eerie glow is not alone. Other clouds in the vicinity have also shown unusual X-ray activity, brightening and dimming in turn. These findings suggest that our black hole may have experienced not just one, but several such flares over the past few centuries. Each cloud that flickers in X-rays is like a page in a hidden diary, revealing another chapter of the black hole's turbulent past. Through these light echoes, scientists are gradually piecing together a timeline of the Milky Way's central engine, a history written in whispers of X-ray light reflected across space and time. The X-ray echoes serve as subtle, short-term memories of the black hole's recent flickers, but the Milky Way also bears more colossal evidence of past activity, signs that stretch thousands of light-years beyond the galactic center. In fact, soaring above and below the plane of our galaxy are two gigantic bubbles of energetic gas, invisible to ordinary telescopes, but glaring in high-energy light. These immense structures, known as the Fermi bubbles, are like faded scars in the sky, hinting at a dramatic event in the ancient past when the galaxy's hidden heart burst forth with extraordinary power. To understand those, we must journey millions of years back in time and imagine the feast that could have blown such giant cosmic bubbles. How many times in the Milky Way's history has the central black hole awakened in such a manner? The X-ray echoes reveal one instance a few centuries ago. The giant bubbles speak of an even greater episode millions of years past. It's clear that Sagittarius A star has a sporadic temper, mostly quiet, but capable of rousing itself to dramatic effect now and then. There may have been other flares and bursts in between, leaving subtler marks still waiting to be discovered. With each clue we uncover, we refine the timeline of these awakenings and gain a deeper understanding of the heartbeats of our galaxy's hidden heart. High above and below the crowded disk of the Milky Way, two gargantuan bubbles of energy billow out into space. Invisible to ordinary eyes, they were discovered as faint gamma-ray glows, each stretching about 25,000 light-years from the galactic center. These are the Fermi bubbles, enormous lobes of superheated gas and high-energy particles that tower over the galaxy like a pair of cosmic hot air balloons. Together, from tip to tip, they span roughly 50,000 light-years, almost the full diameter of the Milky Way itself. They stand as testament to some powerful event that once emanated from deep in the galaxy's core. Remarkably, these giant lobes went unnoticed until 2010, when a space-based gamma-ray telescope revealed their presence. They appeared as huge, faintly glowing masses with surprisingly sharp edges, almost like two cosmic soap bubbles attached to the galaxy's center. Their symmetry above and below the galactic plane was a strong clue that they were blown out from the middle, like the two halves of a colossal hourglass. Such structure and alignment made it clear that the bubbles were relics of a single central engine, very likely a past outburst of our Milky Way's black hole. To inflate structures of such magnitude, a tremendous burst of energy must have been released from the galaxy's heart, Scientists suspect that roughly 5 or 6 million years ago, long before humans ever walked the Earth, Sagittarius, a star, entered a phase of significantly heightened activity. In that ancient epoch, the black hole may have devoured a hefty influx of gas or unleashed powerful jets and winds for an extended period. This intense bout of feeding and feedback would have driven a surge of energy into the space above and below the Milky Way's disk. That outpouring blasted into the tenuous halo of gas surrounding the galaxy, heating it and sweeping it outward. Like twin balloons being inflated from within, the Fermi bubbles rapidly expanded as shock waves carved out huge cavities and filled them with hot, magnetized plasma. Even after the central engine calmed down and the energy flood ceased, the bubbles remained, slowly cooling and fading over millions of years, yet still looming as ghostly echoes of that outburst. For eons they have hung above the galaxy, a testament to the time when the Milky Way's heart roared to life. The sheer scale of the Fermi bubbles is difficult to fathom. They contain gas heated to tens of millions of degrees, and the energy required to create them was staggeringly high, equivalent to the simultaneous explosion of millions of stars. To put it another way, at the black hole's current feeble output, it would take an almost unimaginable length of time to pump out the energy needed to blow such bubbles. Their existence is striking proof that the black hole, given the right conditions, is capable of far more ferocity than we witness today. It stands as a reminder that the quiet engine at our galaxy's center has not always been so quiet. It's intriguing to imagine how the Milky Way might have appeared during that ancient outburst. Perhaps an observer in a distant galaxy, millions of years ago, would have seen our galaxy's core shining unusually bright, with twin lobes of energy extending above and below it. In essence, for a brief moment in its life, the Milky Way could have resembled a mild quasar, advertising the feast of its central black hole to the universe. Now, ages later, the spectacle has faded, leaving only the ghostly bubbles as evidence that it ever happened. Inside those enormous lobes, the gas is extraordinarily hot and thin. Temperatures reach tens of millions of degrees, yet the density is so low that if you were floating inside a Fermi bubble, you'd find it emptier than the best vacuum we can create on Earth. Charged particles zip around within tangled magnetic fields, emitting faint glimmers of X-rays and gamma rays. It's a very different environment from the cool, dense gas in the galaxy's disk, a testament to how powerful the outburst must have been to create such an extreme bubble of plasma in space. The Fermi bubbles show that the Milky Way's core can affect regions tens of thousands of light-years away. Yet closer to home, within just a few hundred light-years of the black hole, the aftermath of its activity can be even more pronounced. This region, known as the Central Molecular Zone, is the bustling downtown of our galactic city, crowded with dense gas clouds and clusters of young stars. Any burst of energy from the black hole sends ripples through this hub, with immediate consequences for the environment there. The Central Molecular Zone, within a few hundred light-years of the center, is rich with interstellar material. It contains numerous massive clouds of molecular gas, orbiting the center in a ring-like structure. These clouds are the fuel for future stars and for the black hole itself. At times, clumps of this material migrate inward, feeding bursts of star formation or providing the black hole with something to devour. The environment here is dynamic. Clouds collide, stars are born and die, and through it all, the black hole sits at the hub, quietly affecting the conditions. When the black hole unleashes energy, it doesn't only send out distant bubbles, it also pours heat and turbulence into this local neighborhood. The result is a kind of feedback. The injected energy can prevent some gas clouds from collapsing into new stars by warming and agitating them. At the same time, shock waves from the outburst can compress other pockets of gas, potentially triggering star formation in a different spot. In this way, the black hole's activity modulates the pace of stellar birth in its vicinity and shapes the overall climate of the galactic center. Astronomers have noted that, given the wealth of gas in the galactic center, the rate of star formation there is lower than expected. It's as though something keeps the gas too agitated or too warm to collapse into new suns on a large scale. The likely culprit is feedback from energetic events, bursts of radiation, winds, and shock waves pumped out by the black hole and by occasional stellar explosions. That injected energy turns the central region into a heated, turbulent zone, effectively putting the brakes on what could otherwise be a runaway burst of starbirth. The clouds remain restless, unable to settle enough to form many new stars. In this way, the black hole acts like a cosmic thermostat, ensuring that the central city doesn't spawn stars all at once in an overwhelming surge. Interestingly, the black hole's influence is not purely suppressive. The same shock waves and winds that quench star formation in one location can compress gas in another. In some cases, an outburst might actually trigger stars to form by squeezing a cloud just enough to ignite it. Astronomers suspect that certain unusually young star clusters near the center may have been born this way, as a consequence of the black hole's past eruptions nudging gas into collapsing. It's a complicated interplay. The black hole can both hinder and foster star birth, sculpting where and when new stars light up in its vicinity. Over the course of eons, the galactic center may undergo cycles of activity, a kind of cosmic rhythm between star formation and black hole feeding. In one phase, gas might cool enough to form stars in a burst of activity, peppering the central zone with new, massive suns. Those stars live hot and fast, pouring out winds and eventually exploding as supernovae, which in turn feed the black hole and prime it for its next eruption. Then, as the black hole awakens and releases energy, it can curtail the birth of the following generation of stars by heating the remaining gas. In time, things calm and cool again, setting the stage for another cycle. This seesaw ensures that neither star formation nor the black hole's growth runs away unchecked. Each keeps the other in check over the long run. Among the most dramatic ways a black hole can release energy is by launching jets, narrow beams of plasma that shoot out at nearly the speed of light. In quasars and radio galaxies, these jets pierce through intergalactic space, visible across millions of light years. One might wonder, does Sagittarius A star have such jets, either now or in the past? If powerful jets were ever launched from our black hole, they could have driven phenomena like the Fermi bubbles and stirred up the central zone. Yet when we look at the Milky Way's center today, we don't see a blazing jet cutting through the sky. If a jet exists, it must be exceptionally weak or hidden, a mere shadow of the spectacular beams observed in more active galaxies. Over the years, astronomers have searched for any sign of a jet from our central black hole. The evidence has been elusive, but not entirely absent. Careful X-ray images from the Chandra Observatory have revealed a slender streak of emission extending outward from Sagittarius A star, hinting at a possible jet pointing in a particular direction. Radio telescopes, too, have observed a faint lobe and shock-like feature aligned roughly perpendicular to the galactic plane, as one would expect if a weak jet had ploughed into the surrounding gas. These clues suggest that a jet does exist, but it is no towering beacon. It is subtle, dissipating its energy close to the core. Why would our black hole's jet be so unimpressive compared to those in quasars? A key reason is that Sagittarius A star is consuming very little material at present. Without a sustained inflow of gas to energize it, the black hole simply cannot power a strong, long-lived jet. Furthermore, the environment near the black hole is crowded with stars and gas, so any jet might quickly smash into the surrounding matter and fizzle out before extending far. All these factors conspire to keep any jet from growing into the kind of extragalactic beacon we see elsewhere. It's also likely that the black hole's jet engine, the magnetic mechanism that launches jets, is idling on low power in this quiet state. Sagittarius. A star could be spinning rapidly, providing the potential for a jet. But spin alone isn't enough, without ample fuel and magnetic fields to tap into. All indications are that if a jet exists, it is faint and stunted, carrying only a tiny fraction of the energy that a quasar's jet would deliver. In the cosmic balance of power, our black hole's output is currently dominated by gentle winds rather than any ferocious beam. While gas and winds provide the black hole with a steady trickle of nourishment, larger prey can occasionally wander too close. Most stars near the galactic center circle the black hole at safe distances, repeating their orbits like planets around a sun. But from time to time, a star, or even a planet, might find itself on a perilous trajectory, grazing the black hole's point of no return. In those final moments, the immense tidal forces would begin ripping the object apart even before it crosses the horizon. For the unfortunate star or planet, it is a cataclysmic end. For the black hole, a rare and bountiful feast. A doomed star would be stretched into a stream of gas, spiraling into the darkness and unleashing a brilliant flare of energy as it goes. Sagittarius. A star, momentarily jolted from its quietude, would blaze brightly during this feast. Even far smaller bodies, like stray asteroids or comets, could incinerate in a flash of X-rays if they plunge inward. Such violent encounters are rare in our galaxy's center, but they showcase the black hole's most destructive potential. They remind us that anything venturing too near the hidden heart will meet an awe-inspiring and final fate. Astronomers have observed tidal disruption events in distant galaxies. These are brilliant flares that, for a few weeks, can outshine all the stars of the host galaxy combined. We have not yet witnessed such a catastrophic feast in our own galactic center, but the possibility remains ever present. If a star were to meet its demise at Sagittarius, the resulting flare would briefly make our galaxy's core one of the brightest beacons in the sky, a dramatic announcement of the event. In the meantime, Sagittarius, a star, exhibits smaller flashes of appetite. X-ray telescopes detect brief flares from the black hole almost daily, sudden upticks in brightness that last only minutes to hours. One hypothesis is that these frequent flickers are caused by the capture of tiny objects, perhaps asteroids or comets, that wander too close and are vaporized, releasing a quick burst of energy. Indeed, in 2013, an especially bright X-ray flare was recorded from Sagar A star, leading some to speculate that the black hole had just swallowed a sizable asteroid or a fragment of a planet. Such minor flares are mere appetizers on the black hole's menu, yet they remind us that even in quiet times, the area around the hole is full of activity on small scales. With all these dramatic processes at play, sporadic feeding, outbursts, winds, even star-shredding events, one might wonder how the galactic center avoids spiraling into chaos. In fact, there appears to be a natural balance at work. If the black hole begins to feed too greedily, the energy it releases pushes back on the surrounding fuel and often cuts off its own supply. Conversely, if little is available to eat, the giant simply stays quiet, waiting until more material drifts within reach. This self-regulating behavior acts like a cosmic thermostat that keeps the black hole's activity in check over long periods. The energy output, in the form of radiation, winds, and any jets, tends to balance against the energy input from infalling mass, maintaining a kind of equilibrium. Thus, Sagittarius, a star, spends most of its time in a low-key state. Over centuries and millennia, its mass grows by only a negligible amount, even as it continuously exchanges matter and energy with its surroundings. It is neither starved to dormancy nor engorged into a blazing quasar, but something comfortably in between, steadily ticking along as the Milky Way's central engine. The Milky Way is a vast system, yet it remains deeply connected to its center. When the black hole at our galaxy's core stirs, the effects are not confined to the central region. They can propagate across the galaxy's disk in subtle ways. One example is high-energy particles accelerated near Sagittarius A star that travel great distances and diffuse throughout the galaxy as cosmic rays. Some of these particles may even reach all the way to our solar system, meaning that an outburst in the galactic center long ago could send a shower of energetic particles that eventually mixes into the space around Earth. Such particles, born in the core's outbursts, can alter the chemistry and temperature of interstellar clouds far from the center. They are like messengers carrying news of the black hole's activity out to the Milky Way's suburbs. Even regions thousands of light years away can feel these faint influences given enough time. In this manner, the moods of the galactic center, its active bouts and its quiescent spells, send ripples through the galactic ecosystem, subtly linking the heart to the spiral arms. Imagine a powerful flare from the center, sending a pressure wave through the inner galaxy. As this wave travels outward, it could compress gas in certain regions of the disk, perhaps jump-starting star formation in pockets far from the core. At the same time, it might heat and disperse gas in other areas, delaying star formation there. The net effect is that a single central outburst might subtly rearrange the pattern of star birth across a sizable swath of the galaxy. Over millions of years, repeated cycles of activity and calm at the core could help shape the distribution of stars and gas, even far from the center, much like the beats of a heart sending pulses through a living body. It's even possible that the Milky Way's relatively gentle central engine has allowed our galaxy to flourish. In some galaxies, a hyperactive black hole blasts out so much energy that it sweeps the galaxy clear of the gas needed for new stars, effectively ending star formation. Our black hole, by contrast, seems to operate in a moderate regime, energetic enough to influence its surroundings, but not so wild as to quench the entire galaxy. This balance may be one reason the Milky Way continues to sustain star formation in its disk while still maintaining a stable central environment. The heart gives energy to the galaxy, but not so much as to burn it out. Our galaxy's hidden heart and its sprawling spiral arms are not isolated from each other at all. They are parts of one ecosystem, each influencing the other. Every flicker at the core, every breeze of particles or dramatic flare, is in some way communicated to the wider Milky Way. Over cosmic timescales, this dialogue between center and disk helps shape the evolution of our galaxy. In understanding these echoes across the Milky Way, we come to see the galaxy as a unified whole, with the dark, mysterious heart at its center, quietly orchestrating cosmic symphonies that play out on scales of light, years, and millennia. As we continue to observe and unravel these subtle connections, we remain vigilant for signs of the black hole's next act. Perhaps in some future era, maybe tomorrow, maybe centuries from now, Sagittarius, a star, will stir again, brightening the core of our galaxy with a new outburst. When it does, the effects will not only illuminate the hidden heart, but will once more ripple outward to the farthest reaches of the Milky Way. For now, we watch and listen, attuned to the quiet giant's breathing, knowing that even in its silence, it binds together the fate of the stars around it and the galaxy beyond.